Welcome, welcome. Thanks for coming to the second annual Air Talk on the Big Sky Symposium. And this date has been circled for a long time. And we're so pleased to have you guys out here present your research today. So we're very pleased to have Dr. Joel Ludus come out from the University of Washington to be our keynote speaker this year. And then we're going to introduce our celebrity judges in just a few seconds. Hellgate and Corvallis will present from 10 o'clock to 11:20. Then we're going to have a lunch. There's some really cool things happening at lunch that Nancy can tell you about. But there's an exploratorium with some really cool stuff, and we haven't even seen it yet. Great lunches, posters, presentations. We have booth setups, free stuff everywhere, so go ahead and check out all the exhibits. Can you hear me better now? This is where we have MCAT filming, we have to use the microphone today. And so anytime anybody comes up here, we have to talk into the microphone. And so we'll hold it like this. We'll do a test run right now. So 12:15 and 12:30, we have a guy in a crazy looking hat. Oh, he's not wearing his hat right now, but that's Garen Smith, otherwise known as Garen the Wizard or Gee Whiz, and he's going to give this pretty cool magic show. And volcano's going to be outside, and one word, fireball. And it's going to be cool. And you'll see exactly what I mean at lunch. And then from 12:30 to 12:40, we're going to have a couple ladies that have participated in the program for the past several years as part of our pipeline, what we call it. We've been working with these students at Big Sky since they were juniors, and now they're working for us here at the University of Montana. So they're going to give a little spiel on their experiences with the program. Big Sky, last but not least, is Big Sky, 12:40 to 1:20. Then we're going to wrap it up and give out gifts, say thank yous, talk about future plans. And again, welcome to the University of Montana. This, we hope to be, is a celebration for you guys. You've done a lot of hard work. We've sampled in your homes, and I'm sure your parents weren't too pleased on some of the occasions, especially with these noisy PM monitors that we have that Big Sky knows about, and Corvallis will know about next year. So, again, this is a celebration for you guys. We appreciate you being here. And without further ado, I'm going to introduce Dr. Joel Ludus. Dr. Ludus is a semi-retired professor from the University of Washington. She works for the Department of Environmental Health, School of Public Health and Community Medicine, and she's a former senior scientist with EPA. Her list of accomplishments takes up more time to mention than we have here available. So basically, if it's a combustion source and it gives off air pollution, chances are that Joellen is an expert on it. So without further ado, let me introduce Dr. Joellen Ludus, and she's going to give you a little keynote address.
Well, I'm very glad to be here. I was a high school student a long time ago in the 60s, early 60s, and thought that I might study art or maybe English. And then in 1960, when I was a junior, I took chemistry. And that was one of the years that the first Sputniks were shot off. It was the time of the hippies just getting started. And the world was very different, I think, than what it is now. At least it seems to me like it was. And I was just fascinated by this young chemistry teacher we had who was very excited about everything going on, arranged for us to see some of the spaceships taking off in real time because it was happening during our chemistry class, and encouraged us to do a science project. So I thought about this and got pretty excited and came up with an idea for a science project and spent most of my junior year and every free moment working in the lab there. And it changed my life because in my experience, studying chemistry and biochemistry is very different than doing it. And I think it's just fantastic that you've had this opportunity to really experience what it's like to do sampling, to be out in the field, to actually conduct research. And I think it may, if it affects you like it did me, it may lead to a real career change. I did get my degree in chemistry, and I added on education in the last 2 years and was able to teach high school chemistry and physics for a couple of years while I started my graduate work, and then finished my PhD in biochemistry. And I've had just a fantastic experience in doing research, mostly once I finished my PhD for the Environmental Protection Agency for almost 30 years. And now I'm working with the University of Washington, but I did collaborate with universities all the way along. And most of my research has been focused on sources. And since most of you will be gone and won't be here for my main presentation, I wanted to give you just a little flavor of the kind of research that I've done. I think I pushed the wrong button here. So like Tony said, I've worked a lot with combustion sources, characterizing the emissions from those sources, figuring out what compounds are signature compounds or tracers for those sources, and then doing ambient air and personal monitoring studies on children and adults to try to characterize not just what pollutant that they're exposed to, which is very important, but when we want to control it and clean up the air, we need to know what is the source, because we really just can't go out there and eliminate a particular VOC or particle-bound organic compound without knowing where that compound comes from, because the way we control it is through the source. Well, over the years that I've been doing this research, too many years, we've moved from the agency, EPA, and the country has moved from regulating pollutants like carbon monoxide to trying to understand and regulate very complex organic gases, volatile organic compounds that you all have been working with, and now realizing what a big contribution semi-volatile compounds are. Those are compounds that are bigger than the ones that you've been working with, and sometimes they're in the gas phase and sometimes they're in the particle phase. And as we study more and more about particles, we're finding out that not only are there big particles and fine particles and respirable particles, but there are ultrafine particles that are so tiny that they almost act like a gas. And of course, probably the most important pollutant to control, if we're concerned about health effects, is cigarette smoking and other smoking pollution, because it isn't just how carcinogenic or how toxic or how potent a source is, but it's how much exposure. So your total risk is really a sum of, or a multiplication factor of how potent it is or how toxic it is and how much you're exposed to. And with indoor sources, when you're in an enclosed room, you have really a lot of exposure. I've mostly studied cancer, but in recent years have collaborated a lot on studies looking at both cancer, respiratory effects, and more recently reproductive and cardiovascular effects. We can characterize and have started to really make advances in all of those areas. So we know combustion emissions and particles and VOCs can have an impact on all of those health endpoints. A lot of times what I'm searching for is what is the magic bullet? What is the compound that's really causing the effects? And then really what are the sources that we can eliminate to get rid of those causative agents? So my husband, who's in the room back here, and myself and another engineer that worked with us, we were the first ones to discover that diesel particles, there's one of our first samples up there in the top left, that diesel particles caused cancer. Of course, we did it first in studies in bacteria showing that it induced mutations, and then did animal cancer studies and cell culture studies. And later went on to do a lot more with wood smoke, and that's how I came to collaborate with some of the folks here in Montana on wood smoke emissions. And some of the emissions that we have studied in depth since then are emissions that we have good human cancer data on, or respiratory effects data on, and that includes cigarette smoke, coke oven emissions, and smoky coal from China. And it was important for us to look at these emissions and to study them in the same biological systems because we have really good human data on them, and we can compare our in vitro studies and animal studies to be able to validate and make estimations of potential cancer risk from short-term studies. And I'll just stop there, and let me see if I can escape out of this, yeah. So that's a little flavor of my work. If you're not going to be here this afternoon and you're interested, please talk to any one of your teachers who can probably get in touch with the group here, and I can send you copies of my papers or presentations or help you with anything you would like to get into that you're interested in. And I just think I really congratulate you for getting involved with this program and getting involved with actually doing research so you know what it's like to be a scientist. It's a wonderful career, and for a woman too.
So Joellen's husband, Bob, go ahead and raise your hand, is a Missoula native and went to Hellgate High School before it was Hellgate High School. What was the name of it originally? What's that? Missoula County. So there you go. The original Hellgator. So. So before we, let me go ahead and introduce our celebrity judges, and then we're going to talk briefly about how we got to this point and move on into the presentations. Starting from my left to my right, we have Russ Thomas, meteorologist at KPAX. Go ahead and stand up, Russ. And it's kind of hard to get over those chairs, but so Russ Thomas, everybody. And it's really interesting that you guys are sitting together. So, meteorologist from KECI, Mark Haka, chief meteorologist for KECI, Mark Haka. And do we have any Grizz fans, football fans in the audience here? Besides myself. So Coach Bobby Houck needs no introduction. Coach Houck, thank you for being here. And Mayor Ingen is here. We're graced with his presence today. Mayor. And I used to love the articles you'd write for the Missoulian several years back. I'm on it. So about the lutefisk and the gastrointestinal problems about the lutefisk. If you remember back, some fabulous stories. Last but not least is Garen Smith, chemistry department professor, otherwise known as Garen the Wizard or Gee Whiz. And he's going to have some really great magic show presentation here in a little while. So a little bit about why we're here today and how did we get here. So really we started a while back, 2003, 2004, and Dave Jones and I went to the graduate school together here at the University of Montana. Garen Smith was our boss. So we were kicking around some ideas on how we could collaborate, and we had a lot of equipment here, and he had a student that was ready to do a research project. So Isaac Schmidt, back in December of 2004, sampled in the homes of 14 of his classmates. Got some really cool data, and we kind of took it from there. So the following year, 2004, 2005, the program really mushroomed. So then we sampled in 35 households at Big Sky, approximately 12 at Hellgate High School, 14 at Corvallis High School, and then 8 or so up at Salish Kootenai College. So almost 85 homes were sampled in year 2 of the program. So all of a sudden we were inundated with data, and this year we really tried to refine what we were doing, making the program better. So again, we're sampling with Big Sky this year. We have Corvallis again, and Jim Strebel is here, and Hellgate again. Melissa Hinthorn is here. And at the very beginning of this program, what we do is we like to go into the schools and we talk about our research. And you'll remember the same exact slide when I came in and talked to your class about air pollution and some of the health effects with that. We tried to sell the program to the students, and we would say, so what does the University of Montana get out of this program as far as you guys participating? And I say it's going to help us determine hot spots of air pollution throughout the Missoula Valley. And I bet you in some of these presentations that you guys are going to present today, you're going to help pin down some of this information. Another way this is going to help us is provide us with research and helping us investigate the relationship between indoor and outdoor levels of these volatile organic compounds, these air toxics, and PM 2.5. We know a lot about the outdoor environments, but 95% of the time we spend indoors. So it's really becoming a huge research area. We know what the concentrations of these compounds are outside, but what about inside where we spend most of our time? The overall goal of you guys partnering with us is to create this humongous air monitoring network that we can use in future epidemiological studies or health-based studies looking at the health effects of high levels of air pollution, specifically in western Montana. And if you remember this slide, let's pretend that we have this humongous database of asthmatics or folks with respiratory disease throughout western Montana. And if it was just up to us, we sample in one place over and over and over. But using you guys, it's basically casting a net. So all of a sudden, Big Sky High School is sampled in areas throughout west of town. Hellgate is east of town. And Corvallis High School, let's pretend that's the Bitterroot Valley. Corvallis High School is south of town in the Bitterroot. So all of a sudden we have this humongous network of air samples collected throughout western Montana, linking that up with the health research that we have ongoing here at CEHS. So it's really using you guys, it's really making for a great study. And it's safe to say this is likely the most studied airshed in the Northern Rocky Mountains. So thanks to you guys. So if you also remember this slide, what do you guys get out of the program? Well, exposure to modern instrumentation and sampling equipment. You guys were using the same sampling equipment that we did, doing the same sampling techniques. And if you were a graduate working as a consultant, an environmental consultant, doing the same research, you would be billing out at 60 or so bucks an hour. So you guys are getting great experience in using modern instruments. Contact with professional researchers. Also, in addition to myself going into the schools, we like to send other researchers into the schools. Curtis Noonan. Curtis? Is Curtis here? Curtis Noonan was here just a few seconds ago. He's an epidemiologist here. He went to Big Sky High School and talked about the health effects of high levels of air pollution. Chris Malaccio will be going to Corvallis here in the next couple of weeks. He's an immunologist, and he's going to talk about the health effects of particulate matter. And then Earl Adams will be going to Hellgate here in the next couple of weeks talking about GPS. And last year he went to Hellgate. So we like to go out into the schools and talk about research related to what you guys are doing and what you guys are studying. You guys are helping us research a real world problem. High air pollution, high levels of air pollution is a common thing here in western Montana. Everybody's seen the forest fires that we have throughout the summers. We all have these nasty inversions that set up almost all winter long. Some areas have it worse than others, such as Libby. Corvallis has quite a bit of inversions down there, lots of wood stoves. So we have these high levels of particulate matter and air pollution. So the next question is, what are the health effects of breathing this? And that's what you guys are helping us find out. So you're studying a real-world, community-based problem. And then this was the last item here. If you remember this from the very beginning, students experience the value of communicating scientific findings to the general public, blah, blah, blah. So back then it didn't matter. It was kind of a blip on your radar screen. But this is what we were talking about back then, 6 months ago, 9 months ago. So this is the second annual Air Toxics Symposium. And this is about you guys. So before we get started, I'd like for us all to give a hand for you guys, the students. Thanks for participating in the program. And we have a great program set up for you guys today, and it's going to be a lot of fun. And with that, we can start with the Hellgate High School presentations. Let me just explain the judging format, too, while the folks from Hellgate come up. So our 5 celebrity judges have an evaluation form that they're filling out per presentation. And they're going to rank the presentations from 1 to 5 based on several different criteria. At the very end, they're going to add up the scores, and then the highest score from each school gets a $150 gift certificate to the UC bookstore. Okay, so it's pretty cool. They have grist stuff and all sorts of stuff, grist pencils and whatever you want, they have it there. So if the Hellgate folks could come up.
Good morning, everyone. My name is Kristen Howe.
I'm Mark Thomas.
And I'm Haley Granger.
And like was announced, we are from Hellgate. We're very happy to be here today. We'd first like to thank the judges for being here. I think everyone in this room is very appreciative of you taking your time to be here, so thank you. With that, let's get started.
All right, for our topic, we chose how your heating system affects air VOCs within your home. Our question was, does the type of heating system that you have in your home affect the amount of air toxins in your home? But first of all, we need to kind of explain what a VOC is. And a VOC stands for volatile organic compounds.
Say what?
In other words, VOCs are toxic compounds that are found in our air or in our water.
The different type of heating systems or sources are electric heating. And that's an electric heater right there. Another one's gas heating. And there's your typical gas fireplace. And then you have wood heating. Most come from fireplace or wood stove. And here's our procedure. Okay, the first thing is to bring the two pumps home. That's the pump right there. Place one pump inside, one pump outside, based on the number. Make sure the pumps are sitting at least 3 feet off the ground. Read the instructions on pumps and make sure to record temperature, date, humidity, times, and GPS coordinates. And we started our pumps at approximately 7 a.m.
You run the pumps for 12 hours, and then we return them to class. And the tubes that took the samples that were in the pumps were then sent to the University of Montana to be analyzed for VOC levels. And then once we had our data back, we reviewed the results, and we also needed to write a survey for our classmates about what kind of heating systems they had.
We then gathered information on the VOC levels of the people who heat their homes with gas, wood, and electric heat. And then we used the data to conclude which types of heating sources cause the overall highest levels of indoor VOCs.
All right, so our hypothesis. We thought that wood heating systems would be the least healthy type of heating system just because they give off smoke emissions. And we kind of figured that electric would probably be the healthiest. When we got our data, because we were working with heating systems, we only needed to look at the indoor data. And so we averaged each person in our class that had a wood system, a gas system, an electric system, and this is the data that we got. In most cases, the wood is definitely higher than both gas and electric. Another way to look at that is in our graph, where you can see the blue line is the wood, and you can see, especially with toluene, that wood is a lot higher.
So our data proved that our hypothesis was correct and that wood heat did have higher levels of VOCs than other sources, and also that electrical was the cleanest.
So along with our project, we thought, well, we're studying, how these heating systems are not healthy for you, so we wanted to do something to study what can you do in your home to make it healthier. So we put a brochure together for all of you, which will be passed out. And it has 4 different types of heating systems that we researched that are alternative heating sources that aren't all that common in houses, but are definitely healthy for you. Hopefully, if you guys are planning on moving or if you're renovating a house, you might find that useful. So that's our presentation, and thank you very much.
Any questions for these guys?
Oh, he's got a question.
Examples were in your set there, in your data.
How many kids do we have in our class?
16, I think.
We have, I think, 16 students in our class. We used only Hellgate data in ours.
Could you put up your graph version of the data? It went by so fast I didn't have a chance to.
Sorry about
study.
that.
The yellow's the electric. The magenta is the gas and the black is the.
Yes.
Thank you.
Yeah.
How many of your samples were in homes with wood-burning devices?
We had 3. One of those students actually isn't in our class anymore, but Haley and I are the other 2 wood users. So.
Would any of these homes be trying to account for cigarette smoke or some of the other activities that may contribute to background contamination?
Our group didn't in particular because we were looking just specifically at heating sources, so we didn't look at that data.
What would you expect the difference to be between a cordwood burning stove versus a pellet stove? Would you distinguish between those two from the study?
We didn't look at the difference between the two, so we couldn't really
Would you
say.
expect there to be a difference?
I would expect like just the cordwood to be more polluting, I guess,
And why would you expect that?
because it's not as processed. I'm not really sure. It's not processed as much, and it has more of the original like stuff in there.
You're exactly right. It also has air forced into it, so it's more efficient combustion. Good guess.
Okay, nice job.
Good morning. We're students from Hellgate High School. This is Garrett Pauls, Will Fletcher, Christy Starks, and I'm Ari Smith. And today we'll be presenting on air toxics and weather conditions and air quality.
And also, we have some cookies that are being passed around. If you could take one if you'd like and just pass it on down the row and to anybody who hasn't received it. All right. Okay. All right. So our experiment is that we were going to be testing atmospheric conditions versus air quality. And so our hypothesis was that there exists a direct relationship between weather conditions, specifically wind, speed, and temperature, and the level of toxins in the air. And so basically what we were studying is that whenever it's windy or when it's raining or when the temperature changes, we were wondering if there was a difference in the air toxins that we have. So.
All right. As for our actual procedure, now, the first thing that we did was, well, just what all the other groups did. We took data, we collected the students' data from both our class and also Corvallis, I believe, from both this year and the past year. And we used data from outside the home, as you would imagine. Keep on clicking. And so what we actually had to do was relate what the students had found in terms of the air quality outside their home and the weather conditions of that particular day. And to do that, we used a weather database called almanac.com. Click again. And so at first we had considered everything, including precipitation and possibly storms or snow or frost. But we ultimately had to reject those things, all variables other than temperature and wind speed, because there was uncertainty in the accuracy in which they were collected. And we did not want to enter any possible complications into this experiment. So having done this, we were able to actually graph average wind speed against the amount of toxins in the air and also average temperature. Now this one is the average wind speed, that's the x-axis, amount of 11 toxins. We did all the toxins that were available, but just to give you an idea. And we looked at each one individually to see if there are any correlations. Go to the next one. And as you can see, there does not appear to be any readily identifiable relationships between either one of these variables and the amount of toxins in the air. Next one. And so that would be our immediate conclusion, that there is not indeed a relationship between any of those variables. But after having reviewed this further, we came up with some possible other alternative conclusions.
When we looked at our data, we realized there were several flaws that were inherent when in the process of collecting it. Unfortunately, we couldn't solve any of these because we were still determining what our project would be while the data was being collected. One of these problems was that while people were collecting data, they didn't tend to sufficiently write down enough information for what we wanted. However, of course, doing that would have required them to stay home all day, record the temperature as it changed, what the wind speed was, what direction it was coming from, and that unfortunately wasn't an option. There was another problem that our data came from all over instead of one centralized location. And because of that, there were several problems. For instance, one person may have been taking samples from up in the mountains. And when comparing that to someone who lives in town, possibly next to a busy street, there would be a considerable difference in the amount of toxins to begin with, despite what the weather conditions might have been.
We would like to thank the judges for evaluating our presentation, and we'd also like to thank all the students from Hellgate and from Corvallis that helped us gather our data. And we would also like to thank Ms. Henthorn for helping us so much during our presentation. The brochure that we handed out to you is how to use the air pumps and how to collect the data. Thank you.
So are there any questions?
We're going to request the same thing, and if we see your data slides just a little bit longer, you're so used to looking at them to advance right past them before I have a chance to enjoy it.
Okay, do you want to see wind speed or temperature?
I'll look at both of them.
All right.
So I need to try to have a little bit more time to study it.
What time of year was this?
This one.
Various times?
Yeah,
It was all year. Basically, we started around in December, I believe.
Of the year before this last December, actually.
So I went to journalism school. Can you talk me through the data you have here?
Yeah, sure. So you can see the 11 chemicals that we looked at. We looked at all the chemicals that were analyzed, but these are just some of them. Now, the ups and downs seem to be almost randomly occurring, and that would, the ups and downs seem to be almost randomly occurring, which led us to believe that this is indeed, these ups and downs are a result not of differences in wind speed in this particular graph, but rather differences in location, in possibly the situation next to a refinement plant or what have you. So that's what we concluded.
Can we see the temperature level?
Oh, yeah. Similar nature. Is that all?
Do you know, is there other research in the knowledge base?
Yeah, our preliminary research actually did indicate that there would be a relationship, at least with precipitation. But as I said earlier, there were some complications, specifically with all the weather databases that we had access to about the precipitation that actually did occur on a single day. For that reason, we had to limit it to just average wind speed and average temperature. And the data that we collected, well, did not seem to indicate anything.
What questions would you like to see added to the survey to help give someone a full understanding?
Well, possibly questions such as the temperature from their house individually, as opposed to, we sort of had a blanket temperature from what weather sites had said, but it varies considerably depending on where you're living, as well as possible sources from the immediate area which could contribute to spikes in the graphs.
I realize these are sort of averages for each chemical, but did you see a lot of variation from one location to another, or was everybody's chloroform number kind of similar, or did it vary a lot?
Because the data was taken, some of it was taken in Missoula, some in Potomac, which in Potomac there's a lot less air toxins than there are in Missoula. So average-wise, that really affected the graph.
Are there any more questions? All right, thank you.
So I'd like to recognize Garrett here. As an offshoot of this Air Toxic Center of the Big Sky program, we've had high school students now working with elementary school students and training them on how to collect samples. And so Paxton Elementary here in town was interested in the levels of these VOCs at the bus drop-off outside their school on days in which parents were idling outside the bus stop, there's bus stops or buses there, versus on a weekend when we wouldn't expect any air toxics. And unfortunately, as many of you know, our instrument went down when we were trying to analyze many of these samples. So those samples were not analyzed, but nevertheless, let's pretend that they were analyzed. Garrett did a great job in working with these guys, and I'd just like to thank him personally for that. So thanks, Garrett. We will go through the samples, analyze, and next year I want you to come back and we'll present that data. So.
Okay.
Thanks
See if
again.
I can make it.
All right. So real quick, how many seniors do we have in here? All right. Juniors, the rest of you guys? Any sophomores? All right, so seniors got ants in your pants, right? So third group from Hellgate, please come on up.
Hello, good morning. Sorry, that was loud. On my far right is Deanne Snyder. This is Robin Green. My name is Brendan Hierro. The title of our presentation is Plants Saving Our Environment, One VOC at a Time. There are brochures. Hopefully you guys are passing them along. Hopefully there's enough for everyone. They explain on the inside all the common VOCs in our atmosphere and the possible effects, along with a little bit of our data and a little bit of an explanation to our conclusion. So we'd like to start out with our previous studies. We found that NASA did a study similar to ours, and they found that plants significantly reduce VOCs in sealed chambers. And we also found out that plants themselves release VOCs. However, most plants do consume and filter out cleaner air than what they put back. And a lot of the common plants that you might have at home include spider plants, snake plants, or most plants that are bug-free and healthy. One study we did find was extremely successful, and they claimed that their VOCs were filtered as much as 50%. As I said before, some plants do produce more VOCs than what they consume. One of those plants specifically is the ficus tree. It has very high VOC emissions, and that includes carbon monoxide and ozone. And the reason for this, we found out, was that plants actually use these VOCs as sort of a defense mechanism against bugs, which is a good reason to keep your plants at home bug-free and, healthy. And here's Robin.
So Our specific question we were looking at was how plants affect the levels of VOCs in a household. And we hypothesized that the more plants you had in your house, the less VOCs you would have in your house. So we first started out by collecting the air samples like everybody else, and we did it for the 12 hours. And we were only using the indoor air samples. And then we handed out a survey to all our classmates. We used the 15 or 16 people in our class. And on the survey, we asked if they could write down how many plants they had in their house, the average size of the plants, and then the square footage of the house. Yeah. After that, we plotted our data. We used Microsoft Excel, and we looked at the relationship between the number of plants in your house and the levels of the top 10 targeted VOCs. And here's some examples of our graphs. They all looked very similar. And this is 1,3,5-trimethylbenzene, which is one of the top 10 VOCs that we looked at. And on the y-axis, we put the level of VOCs in nanograms per meter cubed. And then on the bottom is the number of plants in a household. And we lacked very many, we didn't have enough data really to get any good results. But you can see that there's a huge gap from about 15 plants to 25 plants, and we'll talk about that later, how it could have affected it. And then, so we plotted the data points, and we got a best fit line, and the R-square value that you see in the corner is a value that shows the correlation between the X and the Y axes. And so the closer to 1 it is, the better correlation you have. So if it was a correlation of 1, you'd have a straight line of points. So this is a pretty lousy correlation we got. In the top corner, you can see those 2 points that are outliers. So in the next graph, this is the same VOC, but we took out those outliers, and we got a slightly better correlation. Here's another example of a graph. This is isopropyl benzene. And on the last graph, we were getting the negative correlation that showed the more plants you have, the less VOCs you would have. Here we are getting a positive correlation, so it was showing the exact opposite of what we thought we would get. We still have the outliers on this one, and so when we took those out, we got a little bit better correlation, but it still really wasn't very conclusive.
So for our results and conclusions, we decided that our data couldn't really soundly support our hypothesis, since, as you saw, the data was fairly sporadic and didn't really show a strong correlation between the number of plants in the house and the level of VOCs. And like I said, there's a small negative correlation, but it definitely wasn't strong. When you saw the R value, it was very, very far away from 1. And we figured some of the factors that could contribute to the sporadic data and the weak correlation would be maybe house construction. One student in our class said that her house had just been renovated before she put the sample, the air tube, in her home. So that definitely would have affected the amount of VOCs. And her piece of data was actually one of the outliers that you saw in the graphs. There's also the possibility if a garage was attached, if the garage had paint thinner or paint or other substances that might have VOC emitting chemicals, that would have definitely added to the level. And also, as Brendan mentioned earlier, there are some plants that release more VOCs than they consume. And we could have maybe done a little more research with the students in our class and maybe asked them what kind of plants they had in their home so that we could figure out if that was maybe a plant that would release more VOCs than it would consume. And if we were to do this project again, we would definitely want to get more samples because, as you saw, there was a very large gap between 10 and 30 plants, and I really don't know how that happened. We just didn't have anyone that had 10, 15, 20, 30 plants. And we would also maybe use like a ratio of the number of plants for square footage of the house, and that might give more accurate data. We'd like to give special thanks to Ms. Henthorn for all her help and patience, to the University of Montana for sponsoring this activity and trusting high school students with thousands of dollars worth of equipment. And we'd also like to thank the judges for coming to adjudicate our presentations. And finally, we'd like to thank plants for making our environment more VOC free. Thank you.
Any questions for these guys?
Did it matter what type of plant was in the house?
That's what we were saying.
Cactus versus,
Want to do next time, we didn't really do any research.
I was just going to remark that your difference in direction with the isopropyl benzene may not be just accidental. I mean, we've looked at the volatiles being given off out of the pulp mill. There's a compound called paracymene, which is isopropyl toluene. So it's got a methyl group on the opposite end of the molecule. And that could be a particular compound that a plant might include in its lignin component. So that one might not be accidental. So I thought it was interesting that you brought that one up. Did you check to see of any of your 10 compounds that were on the list if any of the plants were emitting those directly?
No, I don't think we researched that really, so.
If you looked at the list, which ones do you think would be least likely for a plant to emit? If you want to go back to one of your, I don't know if you have the whole list there.
We don't have it all, maybe like chloroform.
Right, that's exactly what you wouldn't expect, is the chlorine compounds that come out of the plants. Those are more caused by human-made cleaning agents. Very good.
Any other questions?
Okay, we're from Hellgate. Last presentation. I'm Carly Morlock. This is Kyle Nelson, Aaron O'Reilly, and Melissa Saxbury. And our presentation is the TAC of the VOCs inside versus outside.
First off, we'd like to thank Will Farrell and the SNL crew for inspiring our intro. So let's get started.
Give me a B. B. Give me an O. O. Give me a C. C. What's that spell? VOCs. What's that mean? I don't know.
Actually, I know. VOCs are the most important outdoor pollutant according to the Environmental Protection Agency. And they quickly evaporate and become both ground and air pollution. But in our presentation, we focus specifically on air pollution. And Carly will give us our hypothesis.
Okay, our hypothesis before performing the experiment was that there would be a more abundant from the outdoor because of the pollutions outside.
And once looking at our data, as you can see, I passed out cookies, and there are only a few blue ones. The blue ones actually represented the outdoor VOCs, and the white ones represented the indoor VOCs, because with our data, we found that there was 10 times as many indoor as outdoor.
Okay, this is our data. We decided to do it in concentrations because VOCs that are very concentrated become carcinogens, which is very unhealthy to people. The EPA states that it should be 2 to 5 times more concentrated indoor than outdoor. But in Missoula specifically, it is 10 times more abundant indoors than outdoors. This leads me to believe that we have a lot of clean air in Missoula, but there isn't very much clean air in our houses. And so we decided to go even farther than just explaining the data, and we decided to find out ways to improve indoor VOCs because we know a lot of ways to improve outdoor. But, so.
All right, like our data has shown, inside VOCs are at much greater levels than outside. So improving them are very important. How we can improve them are maintain a cooling system, fix roof and pipe leaks as soon as possible, use high filtration vacuum bags, and switch to paints, cleaners, and other products with low VOC levels. Improving outside VOCs are also important too, though. And by improving your indoor, we can also improve the outdoor because a lot of VOCs can leak out into your outdoor. And also, you can join our Missoula in Motion project, which is where you ride the bus, walk, or bike, which would help our VOCs outside too.
Also, there have been major leaps for and against air pollution. Just recently, George Bush is lowering the he's lowering the standards for air toxics for oil pollution, but also there has been recent studies about an asphalt that actually reduces VOCs by up to 50% on the outside. So we would like to open up for questions.
Yes.
This is more a comment than a question. I'm on the Board of Health and the Air Quality Advisory Council. We just finished doing a large community survey. Have you heard about this? Where we asked people in the Missoula area, or actually Missoula County area, so we actually went out to Seeley Lake and down to Lolo, what they thought some of the worst environmental problems were. And that survey returned, people were worried about the outdoor air, and they weren't particularly worried about the indoor air. When they gave the same survey to environmental professionals, the results were the exact opposite because of what you found. So we just confirmed what the professionals also did.
Yeah, we would like to put it to a bigger audience as well, though. Any more questions? Okay, I would like to thank the judges and the audience for being so quiet during our presentation. And I would also like to thank our team and Ms. Henthorn and the EPA for providing more data on it. Thank you.
Thank you.
And Will Farrell and Sherry O'Terry, too. So that concludes Hellgate's presentations. Next up is Corvallis.
All right, my name's Ocean Skyrud, and I'm here from Corvallis High School with my friends.
I'm Colin Campbell. I'm Nathan Lee.
Our study was a pretty basic one. We just want to see if using the walking pumps, if students in our class were inhaling like a volatile amount of VOCs during a normal day of school. So our purpose was to determine if on average our high school students are exposed to dangerous levels of VOCs in a normal day at our school, and to determine these values exceed the safety standards for a normal work week, which is Monday through Friday. Our procedure was for each sample, students wore a walking pump with attached sampling tube for 12 hours a day. A lot of you probably had those. These pumps sampled the air wherever the student went during the day for about 12 hours. And pumps were turned off and airflow was calculated in order to convert these values, the values that we got back on the results of VOCs into nanograms per meters cubed. And then here's a picture of one of the walking pumps. You have the input-output tubes, the airflow meter. I think this is something Nathan put in to make us look smart, because this is a bunch of crazy stuff that I don't even, yeah. Obviously. So, it looks like 50% of our day is spent in school and 20 is spent traveling indoors. And 30 is spent outside. He's the little genius in the group. I don't really get that. To figure out our respiratory rates for each individual, we used a spirometer, and that's a picture of it there. And with our procedure for that was, it was used to find the class average for a normal respiratory volume measured in cubic centimeters. Normal respiration rate for an adult at rest is about 15 breaths per minute, and our class average found a normal respiratory volume to be 2,840 centimeters cubed per breath. And then here's Colin here, taking a big blow on the spirometer. And then more crazy stuff. 15 breaths a minute times 60 minutes an hour times 12 hours a day equals about 10,800 breaths per sampling time. And then it looks like we got that into meters cubed per sampling time, came out to 30.672 you'd breathe. That's meters cubed you'd inhale doing that in 12 hours. And then none of the people who wore the walking pumps had a history of breathing-related problems such as asthma, so these values are considered to be an accurate representation of the class. Wear the pump with style. We had some fun with this. Actually, Colin Campbell, he went to Madagascar right before we did this, so when he came back, he had to wear these around. We told everyone in our school he had like a disease from Africa, and they had to test his breath. It freaked a lot of people out. It was pretty funny, though, so we got some good stories going during that time. And then we measured just a couple. We got the results for a lot of things, and then we just used a couple of the main ones. Benzene causes cancer, usually leukemia, and that's through long-term exposure. It affects the bone marrow and blood production, which is, I think, what leukemia does. Causes drowsiness, dizziness, unconsciousness, death at high levels of exposure. It's found in plastics, detergents, pesticides, lots of different chemicals and things. And here is the 4 students in our class who wore walking pumps. The TLV is the threshold limit value and time weighted average, which is that 1.6 times 10 to the 6 is the amount of VOCs you can inhale in the normal work week, that Monday through Friday. So if you're inhaling that much or more, it's kind of a volatile level and can cause some problems. So these are for the day. Each of these bars is for the students. As you can see, Student 3 had a pretty large amount compared to the rest of the class, but even if you take that number, which is about 4,500, and multiply by 5 for the work week, it still doesn't get anywhere close to the volatile limit. So with benzene, no one was inhaling anything too much. Toluene, tiredness, confusion, weakness, you're kind of drunken-like, loss of appetite, hearing, color vision loss, things like that, birth defects. It's found in paints, paint thinners, fingernail polishes, lacquers, and adhesives. And again, one of the students had a large exposure to this. But still it's well below the limit for a volatile exposure in the work week. And then we had ethyl benzene. There's the causes for it. It's found in gasoline, paints. It affects the nervous system in animal studies, things like that. And again, another student, on all of our results, one of our students had usually much higher than the other 3 students for some reasons. But as well, it's well below any volatile limits. 1,4-dimethylbenzene. It's found in air pesticides, which that's used a lot down in the valley for killing weeds and stuff, so that's big down there. Eye tissue, fainting, convulsions, coma, a lot of problems with that. And again, these are pretty high down there, but still, we couldn't find an actual volatile limit for this, but it's still, we believe, well below probably what it is, considering none of the kids are actually sick in our class from anything like that. And then the total exposure for selective VOCs in our class, student 2 had the most out of any one of these VOCs, and that's most likely because we found that student 2 had both art class and woods, so he's exposed to a lot of paints and chemicals like that. And also he lived in Missoula, so he had to do a lot of commuting on the highway, so that would also lead to more emissions and stuff from cars. So overall conclusion is the VOC amounts were under the threshold limit values, so we weren't, none of our students were inhaling a volatile amount of these that could cause, dangerous exposure and stuff. And this is a sum of our class. There's a few kids missing, but we had a pretty small class. Yeah, and the one who had the most next to the Ramones shirt, he's probably gonna die pretty soon. And then our acknowledgements is we'd like to thank mainly Mr. Strebel for all his time and effort spent helping us on this project, and also in the last 2 years. We're going to miss you a lot. Thank you. And also the judges and everyone for coming out and helping us with these things and watching. And also last year's class, because they helped us some with their data and stuff that we got. And then here's some sources we had. And that's it. Thank you. Is there any questions? Yes.
Now, where do you think the bad places in the school would be for a student who have to spend a lot of time? So do you think a chemistry nerd or an art student or somebody in auto shop would be
I think
the worst position?
the art students would be the most, because I had art class and there's a lot of paints and different things in those rooms. And also the woods room is really bad because there's a back room in there that's just like full of chemicals and paint things. It's pretty, like you walk in there and it's pretty nasty. So probably one of those two students had those kind of classes would be at the worst amounts of those. I think he'd be pretty good. I think he'd be good to go. Anything else? Nope. All right, thank you very much.
Okay, I'm Kylie Cheney, and this is Lindsay Ward, and Jeremy Reynoso, and Josh. And we are from Corvallis High School, and we're doing the difference in outdoor VOCs, and we're doing urban versus rural, so Missoula versus the Bitterroot Valley.
Our purpose was to determine if the VOC levels are higher in rural areas or urban areas. And that's supposed to be Corvallis and Missoula, but, you know, it's just how it is, I guess. Thanks.
All right. Okay. All right, and we believe that there will be more VOCs in urban areas compared to rural areas due to increased combustion and other forms of pollution.
Okay, our procedure was students from Hellgate, Big Sky, and Corvallis High Schools took home the air sampling pumps. The pumps were placed at mouth level outside the students' houses. The data that the students gathered with their pumps was sent to the University of Montana, where it was analyzed using GC mass spectrometry. The data that the university analyzed was sent back to Corvallis, where we put on spreadsheets to analyze, and then we also conducted t-tests to determine the significant difference in the levels of VOCs. Every graph in our presentation shows 16 pump samples from Corvallis area and 22 from Missoula. These are air sampling pumps. Beautiful. Okay. Okay, we analyzed 1,4-dimethylbenzene, or C8H10. It is used in polyester fabrics, solvents, paints, and pesticides. It's a colorless liquid at a normal room temperature. It may cause irritation of the eyes, nose, and throat, and high exposure of the vapor may cause severe breathing difficulties. It enters the atmosphere mostly from exhaust, like petroleum refining, gasoline, and it's used as a solvent and a pesticide. That is our graph, and we were really surprised because it shows that Corvallis is significantly higher than Missoula. Yeah, it shows it. It's okay. And then, yeah. Okay.
All right, and we also analyzed ethylbenzene. Some sources of ethylbenzene include gasoline, paints, coal tar, petroleum, inks, insecticides, and paints. And breathing very high levels can cause dizziness and throat and eye irritation. And air containing ethylbenzene is most often found in areas near factories or highways. Okay. And once again, we found that the levels in Corvallis were much higher than those in Missoula, which surprised us because you wouldn't expect that a rural area would have a lot higher VOCs.
Okay, I want to explain the t-test a little bit. like the t-test is mathematical type thing where we, I'm not going to explain exactly how the t-test is done because I know I'd butcher it, but you get a significant, the number, a t-value, and our t-value there is 2.5, and it's supposed to be, with the amount of samples that we have, the value is supposed to be over 2, I believe, to be a significant difference between the two places in our case. And this one is over 2, so it shows that it is a significant difference, and that's through the math that we did for it.
We only did the t-test for 3 different chemicals because they're like the most important, or the most known. We did ethylbenzene, benzene, and toluene.
Okay, if you've read the packets that other groups have handed out, you kind of have a lot of this information, so I'll just say it's another source of pollution. So moving on, please. Again, we have kind of the same data as before, and it might be a little strange, but we'll get to that.
Okay, this is 1,2-dimethylbenzene. It's used in like raw materials, dyes, insecticides, and fuels. It's C8H10, and it causes irritation just like the other ones. And yeah, switch. Okay, once again, Corvallis was higher than Missoula average, and which was also very surprising. Oh, that's me too. Okay, benzene, which is C6. Okay, it's supposed to be C6H6. It's where carbon-rich material is undergoing complete combustion. It's normally from like it's like made naturally from volcanoes and forest fires, but it also comes a lot from like cigarettes and stuff. And Corvallis was also higher, and we did a t-test, which was not a significant difference because it wasn't over 2, right?
Here's toluene. This one's what I know of it mainly from paint thinners. Like we moved into our new house, and there's a lot of that in my new house, I'm pretty sure. But moving on. This one again, we did the t-test on because it's a big one. And there's not a significant difference between our numbers again. I had this one too. It's isopropyl benzene, and there's stuff that happens from having it: cough, dizziness, drowsiness, headaches, sore throats, and unconsciousness. And this chart showing again a lot like the other ones, where Corvallis, and I'm not sure if you realize, but this was from outside, sampling from outside, so these aren't inside, and that kind of has a big thing to do with our conclusions that we make. We'll get to that too.
All right, N-propylbenzene. It's a member of the family of hydrocarbons, which includes toluene and ethylbenzene, and some of the sources include textile dyeing and printing. And it's released into the atmosphere in emissions from combustion sources and from solvent evaporation, landfill leaching, and the use of asphalt. And once again, Corvallis is about twice as high as Missoula. So, and the total average VOCs, we added up all the VOCs, and Corvallis was about 3 times higher than Missoula, which was a pretty big surprise, from our conclusion.
Okay, so based on the results that we have been analyzing, we have concluded that our original hypothesis was obviously incorrect, and the more highly urbanized area, which is Missoula, has a lower average evaluated VOCs when compared to Corvallis. We thought that this may be caused by, we had last year's data, and we also had fires last year, so that, like the natural, like benzene and stuff. We're also in a valley where there's less place for our air to go or to leave, and so it just kind of stays, and
Our data was also analyzed in the winter, where Missoula's was in the fall. So we also had people heating their houses more, like wood stoves and so on. This is our class, well, our group, yeah. And we wanted to thank all our judges, and so, yeah.
Any questions? Of course I have a question. You mentioned that many of these things are found in exhaust. Actually, if I were going to go look for a hot spot in a community, I might go look near a filling station, a service station, rather than a highway. Why might I say that?
Because there's a lot of, because there's a lot of people, there's a lot of gasoline there, and a lot of people are filling up constantly at one of those areas.
Yeah, so when you put gasoline into your car with the nozzle, what are you displacing?
Air or fumes.
Yeah, you're displacing the fumes out of the gas tank. Yeah. And when the truck comes to deliver the whole bulk of gas into the filling station, what does it do?
Yeah, you're getting a lot of fumes.
It displaces all the air in the underground tank. So if you look at how many gallons of gas the filling station sells, you multiply that by 2, and that's how many saturated vapors have been released. So one of the worst cases I've seen in Montana is over in the Bozeman area, where 3 out of the 4 corners are all filling stations, and the neighbors complain to DEQ because of the high levels of these VOCs. So that might be something to consider looking at your data. Yeah.
Thank you.
One more question. Dr. Curtis Noonan in the back there.
You guys, you did a good job of coming up with different reasons why you might have seen the difference between Corvallis and Missoula. But I'm going to force you to think about one more. Given that the 2 different areas were collected sort of by 2 completely different study teams of students, do you think of another reason that might explain some of your findings?
Yeah, it's possible that we could have been maybe using different pumps or a little bit different pumps to sample with, and also there could have been a lot of stuff wrong with taking it home, because a lot of people could have lived not necessarily in Missoula but farther out from it, and a lot of people didn't actually live in Corvallis. So,
and like in Corvallis, I know just from my own community, if we have pumps outside. My own community, there's a lot of pine needles, and we burn them all the time. And, I don't know if they do that in Missoula.
All right, I guess that answers it.
I'm Zach Davis. This is Patrick Monahan, and this is Mike Thayer. And in the first Corvallis presentation, I was the kid that was going to die. Okay, we decided to measure VOCs between old houses and new houses to see if maybe the things that were used, the materials used to build in building new houses would create higher VOCs.
All right, and for our hypothesis, we thought that newer houses would contain more VOCs because we figured the paints were fresher, more chemicals in the air, so we figured that newer houses would contain more VOCs. So then our procedures, as everyone knows, all the students in our class took home pumps and sampled the air, and they were sent to the U of M to be analyzed. Then when the data came back, we interpreted and organized the data, and then we just selected some target compounds to focus on, and we made graphs of the data so that you could compare the older houses versus the new houses.
One of the chemical or the VOCs we measured was benzene,
figured it's a widely used chemical in construction sites, and it has some pretty serious side effects if you're around it a lot.
This is our graph of benzene, and you can see the bottom of the graph is the age of the house, and we have range from 0 to about like 65 is our oldest, and then we have the how much chemicals it's in, and as you can see from our R squared, which is the correlation, the points are pretty much completely random, so there's no correlation from benzene to age of house.
And basically, just like he says, there's really no correlation. The data points are scattered. So from the data we received, it appears there's no connection between old or new houses and the amount of benzene in them.
The next chemical we measured was toluene. This is another VOC that's found a lot around construction sites, and it has extreme side effects if breathed in a lot.
Here again we have a graph, and our R squared is a little better than the last one, but it's still nowhere near -1 or 1. So judging from this, we can also tell that the age of house has nothing to do with the toluene emissions. Yeah, that's a good one.
And just our results, really no correlation, a little better, but still, from here we can't deduce that there's any connection between age of house.
Again, this is just another chemical that was found a lot around construction sites and has extreme side effects.
Here, it looks like the points are a lot closer, but we have that one big outlier out there that probably threw off our data. But according to this, the R squared still shows there's no correlation.
And our results just show that really since there's no correlation from this data, it doesn't appear that there's any connection between old and new houses. So in conclusion, it appears that from the data we have, that there really is no connection between old or new houses and VOCs. Yeah, because just as we've said, all the data was just scattered around and it really didn't appear that there was any connection. So, any questions?
How old were your houses for new and old?
Let's go to a graph here.
Let's see, there's a couple that were 2 or 3 years old, mine's 7. We got a bunch ranging in the area from about, looks like 25 to 40. And then we have 60 and 65.
What's your range? Like, what's considered new from how many years?
We considered our new houses, what was it, under 20?
Yeah.
Like 20 years and under.
But really there was no connection between any of the ages of houses, so yeah.
Are you familiar with any of the published research on outgassing of VOCs from building materials in new buildings?
No, we're not.
Well, the studies show, I think, Bob might be able to confirm that, is it like most of it happens in the first 6 months?
Most of the outgassing from materials, apartments, walls, etc., happens during the first 18 to 24 months after construction. After that, it plateaus and breeds.
All right, any other questions?
I was just going to point out something with doing a trend line. The R squared is set up so that if there's not much variation on the y-axis, if you've got sort of flat line, your R square is going to be always very, very low. You can even have data that presents a fairly tight line, but if it's almost horizontal, the way that particular statistical procedure works, you're going to get a very low R squared. I think your conclusions are correct. And as long as you have a pretty flat line, your R squared is going to be very low.
asked any of the folks, I don't know if you did a survey as well, or actually asked them how old the house was, but did you ask them about if the houses had been renovated? Do you think that would affect the levels?
Yeah, we did in our survey, and that was figured in. I think I don't know how that was figured in.
We didn't have any. I don't think we had any.
It was on our survey though, so.
Yeah.
Any other questions? All right, thank you. Oh, sorry.
I noticed the outlier that's way up there here to us is like the same one. Did you figure anything on that?
It's probably his house.
No, but we didn't figure anything specifically. All right, any other questions? All right, thank you.
Hi, I'm Emily, and this is James Allred and Adam Hooten. Our project we chose to do was, is school safer or is home safer, by looking at the levels of VOCs. Our purpose was to compare the levels of volatile organic compounds in a home and school environments. There's a picture of the pump that we used. Our hypothesis, the VOC levels at home are generally less than that of the levels in the school environment. Our procedure, students, everyone did this. So you bring home 2 pumps, test it about for 12 hours. We also had kids take the pumps around school, so they were going with them everywhere throughout the day. We had the tube sent up to the U, and were tested with the gas chromatograph mass spectrometer. And then once we got the data back, we analyzed it, put it into spreadsheets, and made our PowerPoint. All VOCs are dangerous, especially if the level from the EPA. What? Oh, yeah. Okay, if the EPA, if the level, is broken and you go out of the limits. And one of the VOCs we decided to look at was tetrachloromethane. Oh. It's a solvent for fats and greases, and it was restricted in labs and industrial and educational labs because it was found that it was a bigger cause for cancer. Benzene, it comes from burning fossil fuels. Long-term inhalation exposure causes blood disorders, and you can get leukemia from it. Toluene, it's a solvent, dissolves many chemical reactants, can be used as an octane booster. And here's James.
Can you hear me?
Good.
Good. Okay. These are these 3 types of dangerous VOCs that we use: the tetrachloromethane, benzene, and toluene. The blue is at home, and the red is at the school. We use 17 home pumps and 15 school pumps. And as you can see, the school is much higher in benzene and toluene, and about the same in tetrachloromethane. And this was in nanograms meter cubed.
Next one.
These might have been some of the reasons for the school being higher, whereas you can see the wood shop's a lot higher in the Mr. Sorensen room. I don't know what's up with him. He used a lot of markers. The learning lab's pretty high, and those are some of the reasons that school would be a lot higher than home. And here's our average of the graphs. We use 16 home pumps and 12 school pumps. As you can see, school is 20,000 nanogram meter cubed more than at home, but those amounts still aren't, they don't pass the EPA volatile standards. And yeah, go on. Our conclusion, after we conducted our experiment, the VOC levels are generally lower at home than at school, therefore supporting our hypothesis. And so basically, skip school as much as possible if you want to live long, despite what the teachers say. No, just kidding. But seriously. And these levels are very minute to comparison to the EPA standards, and that's it. Any questions?
No questions. Any recommendations for your school on how to lower the VOCs in the problem
The ventilation in the schools could be. Who asked that question? Should I be facing? Oh, okay. The ventilation in the schools would help a lot to get the air moving around. Any other questions? Oh, the whiz.
So, were the school data from last year and the home data from this year?
We
Or
use.
Did you test the school newly this year also?
No, we didn't on your second question, but the school data was from last year and the home data was from this year and last year combined together and then averaged out.
Okay. And what does Mr. Sorensen do?
Math, he just uses a lot of markers, we guessed. So,
Smelly marker. Yeah. Have you ever tried to sniff a smelly marker? They're wonderful. It might be an interesting experiment to put a smelly marker for 12 hours next to one of your pumps and characterize them as a soil.
okay. Any other questions or comments, concerns, anything? Nope. Okay, thank you.
Go ahead and let her rip.
And just thanks to all the judges. I just wanted to, I forgot about this. Thanks for all the judges and teachers and all the other students that gave us this information. Thank you.
We did ours on volatile organic compound levels between the 3 schools, and we compared them to the threshold limit values. We looked at 2 studies, and the first one was a study published in 2000 by the International Journal of Occupational and Environmental Health. And that study found that volatile organic compounds, or VOCs, had been implicated as causative agents in asthma and building-related illnesses. And another study that we looked at, done by the Environmental Health Prospect in 2003, concluded that outdoor ambient air pollutants exposures in communities are relevant to the acute exacerbation and possibly the onset of asthma, and those studies prompted us to ask 2 major questions. The first question we asked was, how do indoor and outdoor VOC concentrations correlate with the number of reported asthma cases among Corvallis and Big Sky High School students? And the second question we asked was, how did the VOC threshold limit values compare to the average Corvallis, Big Sky, and Hellgate High School students' VOC exposure? All the samples that we did are just from this year. And we believe that Missoula schools will have a larger percentage of asthma-afflicted students than the rural school of Corvallis due to the higher VOC levels, and that Missoula schools will have higher VOC levels outdoors because of their urban settings. All the students at Corvallis that were researching this study used standard sampling techniques, and every student in our class took home a pump and let it run inside and outside of their homes. Air was pulled in through carbon filters and analyzed using GC mass spectrometry, and all asthma values were obtained from the school nurses. Then averages were found for each VOC level, and the data was analyzed in Excel spreadsheets. So we focused our study on 4 highly concentrated chemicals: toluene, benzene, chloroform, and ethylbenzene. The first chemical was toluene, and the concentrations are usually higher indoors from the cause of common household products. It comes from paint, glue, adhesives, cigarette, and cigarette smokes. Too much exposure to toluene can result in swelling of the liver and loss of hearing, and outdoor toluene levels are caused mostly by automotive emission. We found that Big Sky had the highest outdoor levels of toluene, followed by Hellgate and then Corvallis. And when comparing the indoor levels of toluene, Hellgate had the highest levels, followed by Big Sky and then Corvallis. The next chemical we studied was benzene, and benzene is naturally produced by volcanoes and forest fires. It can be found in crude oil, gasoline, and cigarette smoke. Benzene decreases the ability of bone marrow to produce red blood cells, which in time may lead to anemia. After comparing the outdoor levels of benzene from each school, we found that Big Sky had the highest levels, followed by Hellgate, and then Corvallis. But when we looked at the indoor levels, we found that Hellgate had the largest concentrations of benzene, followed by Big Sky, and then Corvallis.
The next chemical we studied was chloroform. Chloroform is mainly used in the production of refrigerants and manufacturing other chemicals. If chloroform is taken in through water, food, or air, it causes significant damage to your liver and kidneys. And when we compared the outdoor levels of chloroform, we found that Hellgate had the highest concentration, Big Sky the second, and Corvallis the least. But a little bit opposite of that, when we did the outdoor, Hellgate still had the highest, but Corvallis had the second highest, followed closely by Big Sky. Okay, after we studied chloroform, we did ethylbenzene, and ethylbenzene is mainly used in the production of styrene, and that is an ingredient in naphtha, fuels, and asphalt. Outdoor exposures can occur near highways or factories that use ethylbenzene. Indoor exposures can occur when there's use of gasoline, carpet glue, varnishes, or paints. When we looked at the outdoor exposures, we found that Big Sky High School had the highest concentration, Hellgate the second, and Corvallis the least. But looking at the indoor concentrations, Corvallis had the highest, and then Hellgate, and then Big Sky.
Okay, and this is a graph of the averages of all of it for the outdoor chemical levels. And Big Sky had the highest, and then Hellgate and Corvallis. And then in the indoor levels, Hellgate had the highest as far as toluene goes, and then benzene and chloroform, but Corvallis had the highest in ethylbenzene. And this is a graph where we compared the percent of asthma cases to the average VOCs that students at Corvallis and Big Sky took in. And we found a correlation between the two because, as you can see, Big Sky has more VOCs and higher percent of asthma, and CHS has a smaller one. Okay, we also compared all the VOCs to the threshold limit value, time weighted average, and which is the amount of exposure a person can have in a normal work day without adverse effect. And as you can see, they have way lower than the TLV. And our results were that Big Sky had the highest levels of benzene, toluene, and ethylbenzene as far as outdoor, and they also had more asthma cases. And on average, VOCs were higher in the Missoula schools, and there's a, oh, we just ended it? Okay. And that's basically what we found out. We would like to thank the judges, our teacher, Mr. Strebel, and all the people that helped us out.
Yeah, go ahead.
Did you have an asthma number for Hellgate?
We contacted Hellgate, and the school nurse said that it was information that she couldn't give out.
Your values for the outdoor air seem to refute what one of the earlier groups from your school found. How would you answer?
Because they used last year's and we used this year's information, and we actually checked all our numbers. We found this out earlier, and we know that ours are correct. So.
Okay, thank you.
And this is Anna Goodsell, Sean McConaughey, Brandy Kerner, and I'm Emily Keegan.
Okay, I think we have one more presentation, and then we're going to go to lunch, and Nancy's going to square us away on what we're supposed to do here.
Hi, we're from Corvallis High School. I'm Sierra Keaton.
I'm Saren Walker.
I'm Lydia Jessup. We did a study of the indoor air quality in public versus private places. Our purpose was to determine the volatile organic compounds the average human is exposed to based on a private versus a public scenario.
Okay, like everybody else did, we took 2 air pumps, one indoor and one outdoor, and we set them out and we ran them for approximately 12 hours. The data consisted of the target compounds such as chloroform, benzene, and they were in the concentration level in nanograms per meter cubed. Thank you.
Our hypothesis was we basically predicted that VOC levels would be higher in public places and lower in private places such as student homes.
Okay, we set up the pumps and then we ran them for 12 hours and then we took the GPS and re-recorded them. The samples were analyzed by the GC and MS at the University of Montana, and then when we got those back, we put them into graphs and charts and analyzed them. The target compounds, there are 5 listed here, but we actually studied 10 of them. Chloroform, it is used to make other chemicals and can also be formed in small amounts when chlorine is added to water. It can cause fatigue, dizziness, and headaches. Provided by OSHA, you can only have, in an 8-hour workday, you can only be exposed to 50 parts per million. Then there's tetrachloromethane, and it's also known as carbon tetrachloride. And it's created when chloroform reacts with chlorine, and it's used as a dry cleaning solvent. Then there's benzene, which is in a lot of glues, paints, and it causes drowsiness and dizziness. And if you're exposed to enough, it can make you unconscious. And OSHA has set the amount that you can breathe in a 40-hour work week as 1 part of benzene per million parts.
Okay, our last compound is toluene, and basically it comes from crude oils and paint thinners and things like that, and it can affect your nervous system, make you have drunken-like actions, and the allowable limit is 200 parts per million.
VOCs in public places, Corvallis High School.
Yeah, sorry.
Okay, here in our graphs, which you'll see later, you will see that our wood shop in our school, and as you can see here, there are students looking around wood particles, glue, which contains benzene. And we found that those were the most commonly found chemicals, and there's the tight bond glue, which contains benzene and toluene, and the lacquer and varnish that contains benzene and toluene as well. So that's why, like in a school area, the kids might be exposed to large amounts of VOCs in a wood shop.
Okay, here's our first graph, and this is all of our private areas put together. This is composed of last year's data from CHS students that took home pumps, and also this year we had about 4 on here from this year. And the one that you see here in turquoise, which is the highest one, is from last year. And she lives in Pinesdale, and we think that one of the reasons why it was so high is because they were painting, or I think they were renovating when that happened. So that could be why that is so high. And so next. And here's our public areas. We did sort of a little experiment with public places other than just a school. So we took a pump to the DMV office in Hamilton, and what are you doing? What did you do? Okay, I'll just talk over here. So wait, it's the wrong one now. Oh wait, no, it's not. Okay, the DMV office is way down at the left side, and we did a little interview with the treasurer, and we found out like what part of the building they're in, when it was renovated, and things like that. So as you can see, it's not high compared to all the other classrooms in our school. The wood shop, of course, is extremely high because they have a lot of paint thinners and whatnot in there. And then again, Mr. Sorensen, who knows about him? So here's our interview.
VOCs in public places. The Ravalli County Administration.
Hi, we're here with Joanne Johnson. She is a Raleigh County treasurer, and we are in the treasurer's office. And we did a air quality test here, and we're going to ask her a few questions. Where are we located in Hamilton?
We're at 215 South 4th Street, and this is the administrative center.
Okay, what part of the building are we in?
We are in the basement floor, and we have 3 stories.
How long ago was this renovated?
It was renovated in 2002, and we moved in April of 2002. So we've been here for 4 years.
Okay. Okay, so here's basically where we're going to answer our question of which was higher, public or private. And according to our graph, after we took the averages of both, we had about 16 public places that we sampled at and about 14 private. So the private places are significantly lower according to this, and okay, next, I guess. Okay, so basically from our conclusions of the 2 previous graphs of all the public and private samples, the office at the CHS contained about 13,541 nanograms per meter cubed less than the office at the DMV, and part of the reason why that might be is because they have a lot more copy machines, papers, pens, and things like that that could add to the VOC levels. And also, public places on average, with our last graph, contained about 76,347 more nanograms per meter cubed than private places. So, however, these values, after we did a t-test, were not significantly different. According to, when you just take averages, they look like they are, but according to the t-test, they're not significantly different. Our PowerPoint didn't exactly get transferred correct, so we had a few edits on here. The t-test, we got a t-value of 0.01122, and The probability table, we found that there wasn't any significant difference in VOC levels in public versus private places. So the variation could be due to extreme differences in the data and the samples that we took.
The public, like when you saw the schools, those were taken from last year, and then the public was taken, yeah, and then like the private was taken from this year. So that might be a different. That might be. Yeah, both. Okay.
Okay. Thank you. All right, and then go back. And then also, just general conclusions. In our school, the wood shop was obviously higher in Mr. Sorensen's room. And then in the private homes, Amber's that lived in Pinesdale was the highest. And overall, both levels in the public and private aren't over the set limit by the EPA and OSHA. So there's our sources. Yeah, that's it. Any questions? Yep. Go ahead.
What were some of the other public places?
Other public places?
Yeah, you mentioned, you said 16.
16. Do you want to just go back to our graph? We had, basically we had the DMV in Hamilton, and then the rest were taken from our school in classrooms, and then also our high school office. Yep.
If you had a chance to sample some more businesses around the community, what might you expect at some of the different locations?
I'd probably put at least a couple in hardware stores, and maybe I don't know, maybe grocery stores and supermarkets, stuff like that. So
I might try a service station too. Or
yeah, gas station probably too. Yeah.
It might be interesting to see what those stores are exposed to.
Right.
Or a drive-in window at a fast food restaurant.
Yeah, that'd be.
That might be interesting.
Yeah.
Or a coffee cart where people are letting their vehicles lay while they're getting their items for purchase.
Okay. Anything else? Okay, thank you.
Okay, so that concludes the first half of the presentations for this morning. Nancy's going to tell us what we're going to be doing during the lunch hour, and we're running a little bit over time, and she's going to tell us what we're going to do now. So, Nancy.
Very good. First of all, what a great way to spend the morning. Let's have a big round of applause for everybody who's already presented. Part of the mission of the symposium is to recognize great efforts like that, and it's been wonderful to watch those things. I commend all of our presenters.
So we have about 12 minutes or so of presentations with Garen, and then Kim Tritz and Emily Weiler are going to give a little brief presentation of themselves and their experiences with the program. So Garen. Gee whiz.
I'll use this for the benefit of the... If I can get it on my pocket here. For the benefit of the MCAT camera. So I'm just going to do a couple of quick tricks. Now, some of you have seen these because I came down to Corvallis last spring. If you don't know how they work, A real easy way to find out is to take my course, Chem 151, when you come here to the U, because I do these as part of my class. Or you can ask the people who were paying attention last year. So I usually try to earn my wizardly title by doing a second-year Hogwarts ink-making spell. I've concocted my potions. I pour them together and say my incantation. When east is east, and west is west, and one flies over the cuckoo's nest, when red is red and pink is pink, make this water black as ink. See, just as simple as that. Whoa. And then along the line of making my demonstrations a little bit colorful, I thought I might make a model of the Missoula Valley here when Glacial Lake Missoula was in residence. I'm going to pour a little bit of a acid-base indicator dye into Lake Missoula, pollute the water a little bit so that we can see a color, swirl it around. Probably have to add quite a bit because this is a big beaker. Normally, if water is near a neutral pH, it takes on a greenish to yellowish color. And we're going to add a base in here and make it distinctly alkaline, and then it should turn purple. The base I'm going to put in is sodium hydroxide. And if it gets basic, it should turn nice and purple for us. When I stir it up here, see, isn't this nice and colorful? My daughter Amy used to like me to do this on the table at her birthday parties. See, I'm going to embarrass her. I don't remember that, she says. And now what I'm going to do is I'm going to do two demonstrations at once. The first thing I'm going to do is I'm going to titrate the base in here with an acid. The way I'm going to get my acid is I'm going to put dry snow, it's not really dry ice in there. As the CO2 bubbles away, it's going to make carbonic acid, which will neutralize the base. And we'll see Glacial Lake Missoula go from purple to blue to green to yellow to orange as it titrates the acid, or as the acid titrates the base. The other thing I'm going to do is I'm going to make an inversion. This is the Missoula Valley. I'm going to have cold air on the bottom. We're going to have warm air over the top. That's what inversion conditions are. And you'll see the inversion boundary right here at the top of the tub. Did I do a good job, Russ? Great job. Just what we needed. So I brought a big brick of carbon dioxide snow, and we'll throw it in there, and you'll see it start to titrate the base. And you'll also see the thermal boundary from the inversion set up right at the top of the tub, just like the mountains a lot of times are helpful in setting up that inversion boundary. Steam from a hot cup of coffee or hot chocolate rises because it's hot with cold overlying it. That's good for dispersion. Hot out in the room, cold in here isn't. Now as that bubbles away, we should see the color change. It usually takes a little bit of time for it to get to close to the end point. I've got another brick down here that I can throw in to speed it up. While we're waiting for that, this dry ice is kind of cold. Why don't we make something really hot? Oop. We'll make a little bit of lava. So this is going to demonstrate why it's so important to recycle aluminum cans. Aluminum really, really likes to hold on to oxygen. And that's the way it comes in minerals. And it takes a huge amount of energy to coax that oxygen off. What I'm going to do is I'm going to put the oxygen back on, and that will release a lot of energy, although I have to use a little bit of a heat source to get it started. What I'm going to do is take iron oxide, which is red barn paint, without the paint part, it's just the pigment, and a little bit of powdered aluminum, and we're going to trade places, trade partners for the oxygen. It's going to hop from the iron onto the aluminum. As it does so, it'll release a huge amount of heat, and it'll be enough heat to melt the iron. Our end result will be a little slag ball made out of aluminum oxide, and inside will be a little nugget of iron. Usually generates a temperature of about 2,500 degrees, hence my spark catching mat up here. So I've mixed them together. To get its attention, I'm going to burn a little bit of magnesium on top of it. So here's powdered magnesium. And I'm going to put some barium peroxide, to add more oxygen into the combustion. This is going to make a little bit of magnesium oxide particulates. So if you see some white stuff floating around in the air, that's what it is. So I'm polluting the air in here a little bit. But I think it's worth it for the visual effect. We'll now put a fuse in it made out of magnesium ribbon, because I don't want my hand anywhere near 2,500 degrees when it decides to take off. And then I'll grab the blob of lava with some tongs so that everybody can see it. Maybe I should turn the lights down for this one here. Oh, see what happened to Glacial Lake Missoula? It has been titrated. Of course, I can make it purple again by dumping in some NaOH. If you don't mix it up, you get all sorts of colors all over the place as they mingle. Here we go with the lava. Anybody's birthday today? Hey, what? So people can see it. Better? You might want to stand up if you're in the back. I don't want to get it too close to the screen. All right. Here's my magnesium fuse. We'll get 2,500 degrees and a little blob of lava. It takes 700 watt-hours to make a new aluminum can to tease the oxygen off, 35 to recycle one, so there's a 95% energy savings. Fire in the hole. Whoa! There go the particulates. See where I have my spark catcher? It looks like we got 3 blobs of lava here. See how hot that is? We'll make them go into the ocean here. Listen to them sizzle. Inside of each one of these is a little sphere of molten iron. There's another big blob. All right, we'll turn the lights back up. And let's pull one of these puppies out. It should be cool now. Boiling away water uses 540 calories per gram of water. Let's see if I can find a good nodule here. Some sand is stuck to the outside of these little blobs. Where is it down there? And if we pop them open, usually there's a slag crust, and inside are little blobs of molten iron. Here's a little, this is a real small one. Trying to see where all the iron went in this one. Maybe I didn't get a real nice one single chunk blob this time. Usually I do. Here's one little one. So you can see that it beat it up because it was in a liquid form. Here's some more little iron BBs that we made. And then there's part of that aluminum monoxide crust.
Well, they look like my filling.
Right. Oh, let's see. How am I doing on time? One more? Let me bring the lights. Oh, I did bring the lights up, but not quite all the way up. I thought the last thing I'd do is, we've got a partially titrated lake where it's base on the bottom and neutral on the top. This dry ice snow floats, so it titrates it down from the top. The last thing I thought I'd do, I need to have dry hands for, though, to make sure I don't drop the flasks. The last thing I thought I'd do is use a little spell to freeze a solution. This is actually going to be a study in nucleation, and what we'll find is snowflakes and raindrops can't fall without particulates in the air because they need nucleation sites. You can get a supersaturated situation. So I've got a supersaturated situation and I'm going to nucleate it. This one is going to be a supersaturated liquid solution, I'm going to provide it with a solid nucleus. My pedometer fell off. Doesn't want to stay on the shorts this time. So what I'll do is use a magic spell that involves Latin, Spanish, and English to freeze it. Medulla oblongata, et echinodermata, chili on a cheese enchilada, help gee whiz freeze this water. Then I snap my fingers, and you can see the ice crystals forming right away. And now in just a few seconds, it's entirely solid. I put a couple flasks down here for our judges. I still have enough nuclei if you want to come down and watch it up close. It's really kind of fascinating. So see what I did was I dipped my finger in the nuclei, and it's the middle finger because you use your thumb and middle finger to snap. So if you put one of these nuclei in, I got 2 flasks here. So you want to drop it in there?
You bet. It's not going to blow up on me. Right?
It's not going to blow up.
Maybe I want to drop it in there. My hands are
Oh,
sweating.
that's right. There, see there it landed. And in just a couple seconds, oh, you actually got 2 in there. We can see 2 nucleation sites. So it quickly sets up. Okay, that's what I had for your entertainment. Now let's have some more good talks about air toxics.
Okay, now we're going to talk about the pipeline that we have established with the high school students now. So I'm going to introduce 2 young ladies that have been working with us for a couple of years now. So I guess I'll start with Kim Tritz. She is a Big Sky graduate. Many of you guys may know her. You guys know Kim? All right. Kim's a superstar. So we started working with Kim as a junior at Big Sky High School. She sampled in her house as part of the program. Then as a senior, she took on the project as a senior project and kind of organized all the sampling for Big Sky. And this past year, she's a freshman at the University of Montana. Now she's continuing to work with us, also doing some work with another graduate student that just graduated with a PhD funded by Stone Container. So she's working with him as well. So this is part of our pipeline where we start working with you guys at a younger age. You come to university if you like it, if you like science and you want to keep working on this stuff, then there's an opportunity for you guys to keep working with us here. So I'll introduce Emily in just a few seconds, but Kim, do you want to get up and just say a couple of words? Kim's on the track team now. Kim is on the track team, and she's...
got an A in my chemistry course, too. That's right.
It was all because, I don't know, Big Sky is real rockin'. They know their chemistry stuff. Tony really said pretty much everything I wanted to say. I did it as a senior project. I tested in my house when I was a junior. This program is awesome. I mean, when I did it as a senior project, I didn't realize it was going to get this big and that there was just going to be so many high schools involved, and just it's awesome. And it really was the pipeline to move on. And I mean, I got a job now, which is nice, and so it's awesome, and it'll be great in the future because I know some chemistry stuff, and I can just kind of continue doing what I'm doing and moving on with it, and I don't know, take on more stuff maybe as I learn a little more, and just keep doing it. It's great. You guys should keep with it too. If you really like chemistry, this is a good opportunity for you to just kind of, I don't know, do what you love to do. So, yeah. Thanks.
So none of the records for the track team are safe anymore for the University of Montana. So Kim is Kim is an outstanding young runner for the university. So next up is Emily Weiler, and Emily has a natural ability to multitask, and we call her the blur in our lab because she comes in, she throws her book down, she gets up, she leaves with another set of books, and she does 10 things at once. Emily was recommended to us by Dave Jones of Big Sky High School, and so she started working with us a couple of years ago, I guess, and has just done an amazing job for us, and she'll tell you a little bit about what she's been doing for us.
Hello, like you said, I'm a Big Sky High School graduate. Woo! And I just finished my 3rd year here at the university, and I've worked with the program for about 2 years now. Started off just organizing and labeling all those dang tubes you guys use, and thankfully worked up to analyzing some of them in the lab, and then spent an entire summer just compounding the data from all the high schools that participated into one database, which was not an easy task. But once that was done, we tied it to some GPS data that we'd got, and I was able to make my first poster and go to my first conference, which was the Children's Environmental Health Summit in Helena. And after that, I started working on using the questionnaires that you students filled out while you sampled and tying that to the database. And I was able to make another poster and was invited to go to the National Conference on Undergraduate Research in Asheville, North Carolina just last month, which was a very exciting trip, a bit of a whirlwind trip, but I was able to go all the way across the United States and speak to people from from universities all over the country, and see what people are doing in undergraduate research and especially environmental studies. And then got back, and 2 weeks later went to the University of Montana Conference on Undergraduate Research. So it was definitely a busy semester, and I also was able to help initiate a particulate matter program into Big Sky High School, which I had a lot of help from Kayla from Big Sky, sitting right there. And I'm hoping this summer to improve on that quite a bit. We have some work to do on the program, but it was a very successful first year, and that's one of my goals for this summer is to make it grow as it goes. Make sure I don't forget anything. That was my semester. That's pretty much where I am right now. This summer I have some goals of hopefully getting some papers written on the research we've done so far. We have a whole year's worth of new VOC data to put together and organize again, and I'm really curious how the particulate matter sampling went and to look into that more. And I especially want to thank you people. I admire and respect all the hard work you put into doing our sampling and actually being out in the field and getting our data. There's, of course, no way I could be going to any of these conferences if it wasn't for you guys. And so thank you very much. I applaud you. And I just hope that you continue with science in the future. I'm a chemistry major, so I'm a little bit biased, but I promise you it's worth it. And this program itself has opened so many doors for me and given me so many great opportunities. I work with the best people in the world, and I hope to continue to work for them as long as they'll let me. And it's been a wonderful project that's just growing, and it's a topic that's of utmost importance, especially to Missoula and the surrounding area. So I think you should be proud that you're involved in such an important topic, and I hope you take away as much as you can from it, just as I have.
So Emily and Kim were paid by us to say the good things that they said. Now, we couldn't be luckier to have these two guys working for us, and they're both going to make great researches, or whatever they want to do in the future, they're going to be successful. So with that said, I'm like a proud pop. I just shed a tear here. Let's bring on Big Sky for the 40-minute presentations, and after that we have conclusions and final awards.
Hello, I'm Stephanie Seawald, and our group is Amy Smith, Megan Taylor, and Jesse Ponton, and Cheryl Fredericks down at the end. So basically the title of our project was the correlation between BTEX compounds and residential areas. A little bit of background on BTEX compounds. We wanted to look at these specifically, which are benzene, toluene, ethylbenzene, and xylene, because they're kind of the main compounds in these VOC groups, which you've actually heard a lot about. They're found in gasoline solvents and plastics, and they're used to increase octane readings. Health problems that are caused by these BTEX compounds are bone marrow damage. They're known carcinogens for the most part. They affect your reproductive organs, and they cause fatigue, headache, appetite loss. So basically, our main question with this research was we want to know why some houses' concentrations of BTEX compounds outside are higher than others. And so our hypothesis was this. It was based on location. And so homes that are located closer to major roadways would have more higher levels of these compounds than homes that are located farther away from these areas in more remote places.
So basically our procedure, we began by just looking at some of the information out there about BTEX compounds, which we just presented to you guys. Then we used the data that we all helped to gather around Missoula. We used the numbers that were from our houses. We needed to have all of the houses located on a map, so we had each of the students at Big Sky locate their houses. We had right around 40 people in our classes, so we had a larger number than some of the schools earlier. Then we calculated the averages of the BTEX compounds, and to do that, we took the, because we were just dealing with outside, we just calculated, because there were 2 tubes, and so we just added them together and then divided by 2. But we had originally planned on using both the fall and winter information that we had gathered. However, a lot of the stuff didn't come back for the winter information, and so we ended up eliminating that and just using the fall. And finally, we had to interpret what we had found. So we took the 5 highest levels of the houses, and actually, interestingly enough, we all calculated, we each had a different compound that we were calculating for, and all of us found that the same 5 people had the highest levels, and that was really interesting because we thought that maybe we'd have to go with, maybe one was higher in 3 areas out of the 5, and another was only at one of the highest in 2 areas of the 5. So that was really neat that we had all found that. In this table, you can see the house. We gave everyone a number just by whichever number they were to put their name on the, or their house on the map. And then you can see the different levels up here, and you can see house number 4 for the toluene had an extremely high number in comparison to everything else. And we kind of hypothesized that maybe that was because these were outside samples, again, maybe someone went by with a lawnmower that day while it was being sampled, or maybe someone was painting in that neighborhood. Just all, you know, there's so many variables out there for outside stuff. And also, as you'll see in a minute, house number 4 is located next to a major roadway for Big Sky High School. Then these are the low-level houses, and again, these were, all 5 of these were found to be the lowest. We actually eliminated one house from our data because it had very, very few numbers come in for everything. So we weren't quite sure why that was, and we just decided that we couldn't really use that. Its numbers were extremely low, just like 7 or 4, just really, really, really low. 35 was still pretty low, but most of the numbers did come in for that, so we decided to keep that in our data.
We then plotted all the houses on the map that were for the high and the low compounds. So as you can see, the red are the high numbers of houses, and the green are the low. The red tended to be in like more populated areas where there would be a lot more traffic, and the lower houses tended to be spread out like up Grant Creek or out in the Big Flat area. So there was a lot less travel there and a lot more room for stuff to spread out. And house number 4, as you can see on the map, is it's right by South Avenue, and it's on Central Avenue, which almost every Big Sky student drives down Central Avenue on their way to and from school, and so their outside levels are probably going to be really high for these BTEX compounds.
All right, so based on the results of our data, we concluded that the homes that are located in a high populated area near major roadways have higher concentrations of the BTEX compounds.
Some things that we thought might have been a problem in our study, we were not looking at the weather of the days that people sampled, and that could have had a huge contribution because if it had rained the day before, maybe stuff would have been picked out. If we'd had an inversion, you know, that obviously makes the air a lot worse. And so that was a large factor that we didn't consider. Also, the places we obviously don't know any of the activities that had been going on around that house that day, so there might have been something for some reason that would have boosted some of the levels. There might have been problems with sampling. Again, we eliminated one because we kind of thought that there might be some problems with that because there were extremely low levels. Just regular human error because we all make mistakes. Anything could have happened with that. Also, we did not clearly define what a major roadway was. We just kind of went by our knowledge of what happens around Missoula County and where cars are. And finally, if we could do this again, I think it would be very important to have more samples because we could only take the top 5 from each of the top and the bottom 5 from each one, because if we took any more, we were getting down into that average range because we didn't have enough samples. So more samples would just be more conclusive data. And these are our references. Thanks, and are there any questions?
You would never guess this, and I was going to ask a question. Why do you think they have an expression called BTEX? That's something you find in the books on air pollution, right?
Do you want to talk about it? Or do you want me?
I would like to BS on it, yes. Basically, BTEX, you know, it's kind of easy just to state it that way. And also those are the main target compounds that come off the aromatic ring of benzene. So, yeah, I think.
It might be because they travel together.
And that as well.
Yeah, that's fine.
It's a nice click, so they always come together. So what you just discovered is what caused the scientists to group them into that little acronym. Then I might ask, boy, that must be a really bad house. It's location number 4. I wonder if the student that did that sampling might have been.
Actually, that was not our house.
What is close to our house?
We're very close to a filling station, but our numbers were not very high, and Reserve Street and South Avenue.
Right. So, depending on the wind direction, we could have influence from the holiday station.
Any more questions?
One more. How would you see if the toluene at house number 4 was really out of whack with respect to the B and the E and the X? Is there something you can do with your data to see if that's really out of whack?
Probably. Would you like to tell us about it?
You might want to ratio the compounds of each house and then look at the relative abundance of them with respect to each other. Because you had a higher level of benzene at that location too, that would help damp out the difference just in the main level and let you look at the proportions of each other.
Yes.
Amy, are you thinking about going out of state for college?
Yeah. Are there any more questions? Yes, yes.
The samples you took were not on the same date or on different days?
Right. We only have a limited number of pumps, and so there were some samples that were collected on the same days, but the majority, there would be like 3 samples collected on a given day.
Did you need to tell Tony to take more pumps?
Tony, we need some more pumps. We need more money from the boss.
Anything else to read it?
Thank you.
All right. People hear me? All right. So the title of our page, or of our project, was Inversions and Their Effect on Automobile Pollution. And we ended up having to make some stretches as far as the inversions, but hopefully not too far. So we have some realistic things. Our names, I'm Drew Sheehy, Stefan Lecitra, Don Alsbury, Jordan Taylor, and Cal Galich. All right. So the question we're presenting is there a direct correlation between the BTEX compounds and weather conditions? Basically, we're trying to develop the relationship between inversions and particulate matter levels, which obviously should be pretty closely related. Everyone knows that when there's an inversion, there's more stuff in the air and it needs to be cleaned out, but we wanted to prove that more definitively. So, like I said, our hypothesis was that the particulate levels are going to rise when there's when the particulate levels rise, also the BTEX levels rise, and these should be related to inversions, though we don't have direct inversion data. And we figured that through the 4 BTEX compounds, it would be present.
Okay, these are just all the compounds that we studied in relationship with our project. And all these compounds are found in like solvents and plastics, but we were only concerned with them because they're also found in like automobile pollution, which is kind of the focus of our study. And so benzene here is also a natural part of crude oil, gasoline, and cigarette smoke. And some side effects of coming in contact with benzene can result in death, and it also can cause drowsiness, dizziness, rapid heartbeat, and headaches. And for all these compounds, you'll see like similar side effects for them, and they pretty much all have pretty severe health effects if you have prolonged exposure to them. And our next compound is toluene, and again, it's common in most automobile exhaust. And it's easily absorbed through the respiratory system, and high levels can cause sleepiness, dizziness, unconsciousness, and even death. Our third compound is ethylbenzene, another aromatic compound, and it's found in petroleum mostly. It's found in other things, but we were concerned with that. And again, dizziness, eye irritation, and nausea. And our third compound is xylene. And actually what we were really focusing on were the para and ortho conformations of 1,4-dimethylbenzene. But since the para, ortho, and meta conformations combined makes xylene, we decided to refer to it just as this compound. And it has some of the same similar side effects. And again, it's commonly found in automobile gasoline.
All right, this is the first of some of our graphs. This is just kind of an overview. It shows the particulate matter in the valley at certain times. I think it's from like October to February. We have more data, but this is like what we chose for it. The peaks display, maybe we thought like they could be inversions because it looked like there was more stuff in the air at this time.
All right, so I was in charge of the benzene concentration. And what we did is the blue line on the graph is actually, is that the indoor? Yeah. It's the indoor levels of that. And what we did is we went through all the days and we averaged everybody's date for this, the inside and outside, their levels of the particulate matter. Yeah.
All right, I did the toluene levels, same sort of thing. We have the dates. We just have 1 through 12, but they're just randomly, not random, but semi-random every 5 or 6 days from October through January, early January. And once again, the inside peaks and the whole inside line is above the outside line, which you'd kind of expect because indoor levels are going to be higher. And not a whole lot of peaks, they coincide with one another, but not necessarily with the overall particulate matter, which is kind of against what we wanted to happen, but I'll explain that a little bit more in the discussion.
And this is ethylbenzene levels. They were averaged. We had 2 tubes, and each tube had to be averaged, and then each person had to be averaged that collected on that day. And some towards January, actually, there weren't entirely 3 people because some of the data was iffy. Who knows why? So those were thrown out. There's also not prevalent in any of these graphs so far, but there is a break between December when we weren't testing. So.
And the December break was on account of Christmas break, so we didn't have any sample times. Xylene, once again, sort of the same sort of deal. The peaks generally coincide with one another. Inside is higher than outside, but again, not really going along with the overall particulate matter, so we aren't sure whether it's following the trend that we were looking for. Conclusions, in theory, our project was pretty solid, but once we got through and started doing the data, we couldn't really come up with much of a correlation between the overall particulate matter and what we thought should be the inversions along with the specific compounds. And also there was a wide variation in different data. As we've seen throughout the day, a lot of the lines of normalcy, or rather the lines where it should be, where the data was very varied. Well, very varied. So no valid conclusions can really be made at this time concerning the BTEX compounds, but hopefully in the future, if there was more data collected and more specific things as far as the inversion data, we could come up with something more statistically solid and maybe more complete conclusions. Thank you, and are there any questions? Any at all? Yes, sir.
I may have been eating my brownie instead of paying attention. How did you overlay the air data with the concentrations of the compounds?
As far as...
I saw the air plot, and then I saw concentrations of the compounds. Were those the same date order as the air data?
Yeah, it was all the same. It was all the same dates, as I said, from October through January.
But how can we compare the concentrations to the air data?
Oh, you mean overlay the two graphs together?
Right.
Yeah. Obviously, it would have been nice if I would have done that. I hadn't thought about that until this morning when I saw other people doing that, so would have been a good idea.
I was going to say, boy, I didn't look at the air one.
Yeah.
The air data close enough to remember.
Yeah. Tricky to have a photographic memory, yeah. Anyone else? Not looking like it. All right, thank you.
Okay, we chose to study the naphthalene levels in Missoula housing. And I'm Hannah Lumphrey. This is Mariah Coley. We have Jackie Spade, Jessica Schoening, and Jessica Winters, and Kayla Schoening. Oh, I'm spacing out. So the background of naphthalene. The EPA has classified naphthalene as a group C possible human carcinogen. Other reported health effects include hemolytic anemia and neurological and retinal damage. Exposure to naphthalene happens mostly from breathing air contaminated from the burning of wood, tobacco, or fossil fuels, industrial discharge, or moth repellents.
Okay, so why naphthalene? Because of the health effects due to exposure to it, levels of naphthalene should be noted. Data from my fall 2005 Missoula air quality study show either relatively high or very low naphthalene levels. Why did this trend occur was one of our questions, and what are some possible emission sources within the study area?
Our hypothesis was the naphthalene levels in the representative data may suggest possible sources from which naphthalene is emitted. The high or low trend in the data could be explained by the presence of acute sources of naphthalene emission.
And so part of our procedure was just to pick basically our 5 data points from our sampling as kind of representative data of the entire set. And so we are students 1 through 5, and just right here I wanted to note students 2 and 5 student 2 has really low levels and student 5 had really high levels within this small set. And so within our set of data, we self-reported our own possible sources of naphthalene emissions. And you can see student 2 had a lot of possible sources while student 5 had very little, which kind of goes against our hypothesis because student 5 had the highest levels while student 2 had the lowest.
All right, so in conclusion, a correlation between pollution sources and naphthalene levels was inferred. While the hypothesis appears to be verified, the data also strongly suggests that the condition of the structures tested is a better indicator of naphthalene levels, and eradication of emission sources may significantly improve air quality in the Missoula Valley. Those are our references.
Is there any questions?
Questions?
No questions. Yeah, thank you to the judges and everybody else for sleeping through our presentation.
Hi, everybody. We also did naphthalene, but a little different study of it. That's Elise Bassan, this is Tyler Wisby, and I'm Molly McGrath. So what we did a comparison of naphthalene levels in different areas of Missoula. Go ahead. Okay, so our question was, why are naphthalene levels higher in the Mullen Road area than the Big Sky Target Range area? And after everyone went and tested at their houses and we looked at the results, we noticed a trend that usually the students who we knew lived out Mullen had higher naphthalene levels than the students who lived around Big Sky. So first of all, why we chose naphthalene, which you pretty much just heard, same reasons they did. But it's a possible carcinogen, and other names for it are tar camphor, white tar, and moth plagues. It's used in like mothballs. That is what it comes from, and oh yeah. And it's white solid crystals, and it has a strong odor of coal tar. Go ahead. So our hypothesis was the reason behind the higher levels of naphthalene in the air of the residents of Mullen Road and surrounding areas is that there are a number of factories in that area, and they possibly could use naphthalene and emit it into the air. So our procedure.
All right, well, the first thing we had to do after everyone took home the pumps to their house and collected the data, we had spreadsheets of all the information. So the first thing we had to do was locate each person, like where they lived, and find out who lived in the Mullen Road areas and who lived closer to Big Sky and in the Big Flat areas. And once we did that, we recorded the naphthalene levels inside and outside in each of the individual homes. We found the average naphthalene levels in each area, and then we researched the possible sources of naphthalene, that factories that could be around the Mullen area that would be emitting naphthalene into the air. And then we made correlations between the sources of naphthalene and the high levels of that chemical in the homes.
Okay, and so here are our graphs. After we got the inside and outside, we recorded all the data, and then we had like 12 houses from the Mullen area and then 12 houses from the Big Sky area, and we took the average inside and outside values for each. And so as you can see in this one, the average inside values from the top tube or whatever, the Mullen Road is in the blue and the Big Sky is in the pink, and you can see it's higher, considerably higher. And then the same thing with the inside bottom ones, it's also higher in the Mullen. And then this is for the outside pumps, and it shows the same thing, that the Mullen Road levels of naphthalene are higher than the Big Sky area. And sorry for going too fast through the graphs. And these are the average bottom outside. The top and bottom things are just like the top tube and bottom tube. Same thing. So those are the concentrations. So both in the inside and outside concentrations, both of the levels of naphthalene were higher at the Mullen Road area. So we were wondering why, and so we did some, we did some research, and this comes from the EPA website, the EnviroFacts Data Warehouse, and this is from a study of chemicals released into the air by the Smurfit Stone Corporation in 2004, and like stone containers just right out the end of Mullen. As you can see, like in the bottom one especially, there's pretty high levels of naphthalene released into the air. And since that's right on Mullen Road, that was probably a major source of naphthalene. And so our conclusion is that through our research, we have concluded that our hypothesis is correct. The naphthalene levels are higher in the Mullen area due to the emissions made by Smurfstone in particular, or other plants out there also. There's some more, but that's the one we focused on. And that's it. Thanks to the judges and everyone. And are there any questions? Oh, surprise.
When I've done air sampling for naphthalene, things that I usually look for were how much diesel traffic there was. Because naphthalene seemed to correlate well with diesel. You know, think of Mullen Road versus South Avenue. Would that suggest the same trend you saw?
Probably. South that Mullen Road, like there's more probably semis going down by like North Reserve and more construction out there than out in the Big Sky area.
I would guess it's more diesel truck traffic on Mullen Road.
Yeah.
Good source of naphthalene is creosote. If you have creosote in timbers, they were used in doing raised flower beds or landscaping. Creosote is about 85% naphthalene. So that might be another thing you want to include on a survey if you're studying naphthalene in particular.
Anything else?
Afternoon, everybody. My name's Dave Driscoll. This is Jeff Knight on my right and Jake Robertson on the left. And apparently naphthalene is pretty popular today, but we looked at it a little bit differently. We just took the outdoor fall and winter levels and kind of compared and contrasted the two. So here's Jeff.
All right, I feel a little repetitive saying this again, but this is just an explanation of what naphthalene is. There's a picture of it right there. It's an aromatic compound formed when two benzene rings are fused together. And what is it used for? A lot of different things. Usually it's converted to a thing called phthalic anhydride, which is used in solvents, dyes. Naphthalene is also used in plastics, but the big use is probably you all know what they are. They're mothballs. Major sources of naphthalene in Missoula, mainly insecticides and diesel fuel. Okay, how do fall and winter levels compare to one another? This was our basis of our project. And we basically went through everyone's data and tried to compare their levels that they took at their house from the fall and winter to see how they compared to one another. Is it sufficient? The quantities to be a health hazard? Well, the EPA doesn't have a exact level where they say, you know, this is where it's, you know, bad for your health. They do say, though, that it's possible carcinogen, and in large enough quantities over an extended amount of time, it can cause serious health effects. All right, and right there's our hypothesis. We suspected that in the winter, the levels would be higher than they would be in the fall. And this is kind of what I just said. EPA said naphthalene is not considered to be a serious health risk, but it is known as a possible carcinogen. And what we did is we took everyone's data. We got these big spreadsheets, they're packets from winter and fall, and we analyzed all of them. We took out and we organized them in a graph. And this, what do we got for results? For the most part, everyone's was higher in the fall than they were in the winter, but there were a few where they were slightly higher in the winter, except for this one right here, which is kind of our outlier for some reason. We don't know why. The winter was much higher, and we didn't really know why. We hadn't been able to, so. All right, go ahead. Okay, this is our results. From the information we gathered and we graphed, we could just take out of that for the most part in the winter, the levels are less than they are in the fall, and we have a pretty idea why that is. And we did 20 samples because, as someone stated earlier, some of our data kind of didn't come out right for some people, so we weren't able to have samples from both winter and fall to compare, so we only ended up coming out with 20 total that we could use. And out of the 25 of those, which would be the 25%, were higher in the winter, and the other were the 75%. The other 15 people had it higher in the fall. And it's kind of went against what we predicted. We predicted due to like inversions and stuff that the naphthalene levels would be higher in the winter. Oh, what?
And again, some possible reasons for that. You kind of got to look at where the naphthalene is coming from. Possibly diesel fuel, agricultural use. Fall, everything is still going, but it's starting to wind down. And by the time winter comes around, activity slows down. And that's a possible reason we're seeing less naphthalene in the air.
Questions, anyone?
Yeah. So, what kind of a compound is naphthalene compared to something like benzene? If you looked at it, what would be the major difference that you noticed?
Well, it.
Twice the mass.
Yes.
So how about the state that naphthalene is in compared to benzene?
It's usually found in, well, they have to manufacture it from coal tar. It's not found naturally like benzene. And it's usually a solid, but it sublimes at room temperature, so it can become a vapor. And that's one of the reasons it's kind of bad too. Also, when it becomes a vapor, it's very flammable and explosive, so it's kind of dangerous.
So it's a solid much more than the benzene or xylene, which are liquids of room temperature.
Yeah.
What phase did you capture your sample at?
Well,
In the gas.
yeah, in the gas phase.
So how about the temperatures in the fall versus the temperatures in the winter?
In the fall, they're warm enough to allow the naphthalene to sublime and become a vapor, while in the winter they're
So do you think
far
the
colder.
vapor levels would be higher in the fall than in the winter? Might be interesting to plot that versus temperature rather than versus season, and that might draw out that particular thing.
Any other questions?
All right, thank you.
Thanks a lot.
Good afternoon and welcome again after lunch, and we are ready to go with our presentation. And the title is Potential Sources and Exposure Implications of 1,2,4-Trichlorobenzene. Before we get started, I'd like to introduce my group members. First off, my name is Audrey Schulte, and I am planning on majoring in business management with a minor in chemistry. Next is Shelby Zentner, and she is planning on majoring in chemical engineering. We have Emily Kobus behind me, and she's planning on double majoring in cell biology and biochemistry. Next is Natalie Dial, and she is as well planning on double majoring in biology and dance. Ember Hansen, and she is planning on double majoring as well in neuroscience and music theory. Last up is Kayla Hayden, and she is planning on majoring in biochemistry. What we plan to do with our presentation is attempt to establish correlation between 1,2,4-trichlorobenzene and the location in the Missoula Valley, as well as possible sources. In addition, we will discuss potential effects of this compound. The procedure is not discussed in our presentation, as our sampling procedures remain constant with the rest of the other groups. Before we begin, I would like to hand our binder off to our judges, which includes more of our data and more of our analysis. And so as we begin, I will hand the mic off to Kayla.
Okay, so to begin with, our problem. So the objective of our problem was to explore the sources and effects of 1,2,4-trichlorobenzene.
And there's a particular reason that we chose this compound. When we got our fall samples back, there were only a few select houses that contained this compound in the sample. And some of them were only shown outside, some of them were both inside and outside, and some of them were only inside. And that's why we chose this compound, to target it and to see if we could find potential sources and the causes of it.
Okay, and up next is our hypothesis. And our hypothesis was to find that there was a connection between the concentration of the sample and the location of the household in the Missoula Valley.
And we actually have a map here that's probably really going to be hard to see for most of you. But all of the red dots are the houses that contained 1,2,4-trichlorobenzene. And as you can see, all of the samples are on the western half of the city, being as the students that attend Big Sky live in the western half of the city. So the green ones are houses that had both outside samples. The yellow are the high samples, and the blue are both inside and outside samples. And when we made this map, we actually were looking for a correlation between 1,2,4-trichlorobenzene and the other chlorinated compounds, which include 1,4-dichlorobenzene, cis-1,3-dichloropropene, and chlorobenzene. And there wasn't a whole lot of data for any of those three compounds, so we decided to omit that part of our project, actually, just from lack of data, and focus more on these.
So our results showed that our data wasn't complete enough to prove or even disprove our hypothesis, so we altered the hypothesis and we changed it to find a better conclusion as to why 1,2,4-trichlorobenzene was detected. Our second hypothesis stated that the levels of 1,2,4-trichlorobenzene were detected inside because of a high use of cleaning products, or they were stored near cleaning products.
So after we changed our hypothesis, we decided to focus in on our research. It consisted of just finding products that contained this compound, and also researching some of the implications of the compound, such as the environmental and the health implications as well.
Okay, so 1,2,4-trichlorobenzene is most commonly found industrial uses were like, I don't know what that's, dielectric fluids, synthetic transformer oils, lubricants, heat transfer mediums, and insecticides. It was once used as a soil treatment for termite control, but this is no longer the case, as is it has some pretty severe health implications.
Okay, some of the industrial and domestic uses of our compound. It's used as like wood preservatives and drain cleaners, and used to like just clean stuff. And it was used as an intermediate in the manufacturing of herbicides and high chlorinated benzenes.
Okay, so this is, all right, the environmental effects. So if 1,2,4-trichlorobenzene is released into the soil, it will be expected to absorb the organic matter in the soil. And it will then transfer into our groundwater, which is not good because we drink that. And it's non-biodegradable and in contaminated groundwater. So, but if it's in surface water, it will evaporate with a half-life of 22 days.
Some more environmental effects is it will be subject to reaction with photochemically produced hydroxyl radicals with an estimated vapor phase with a half-life of 18.5 days, and it will not be expected to be subject to appreciable direct photolysis.
Okay, so some of the short-term consequences of being exposed to this compound. It changes the function of adrenal glands, and as well as functions of the kidney and liver. Long-term exposure implies increased adrenal gland weights and contributes to respiratory tract disruption. And even more prolonged exposure is characterized by tremors, narcosis, and high blood pressure.
It causes malfunction to the gastrointestinal tract, and it is also considered to have teratogenic effects, and ingestion of an ounce could prove fatal.
Okay, we found that the samples contained amounts of 1,2,4-trichlorobenzene because they were near cleaning supplies. Yet, to make this conclusion more precise, it would be necessary to obtain more samples and information of the sample locations across the Missoula Valley. Yet, one of the cool things about this is our whole team is composed of juniors. And so next year we will be able to take the time to work with Mr. Jones some more and really focus and extend this project, as well as become more actively involved with just this whole project together. And before we end, we would like to thank Mr. Dave Jones for putting up with us and everything that we put him through, as well as all of the families that had to put up with all of these devices in their homes, which were noisy and sometimes a pain in the rear. And we would also like to thank our panel of judges for being here. So thank you very much. And now we would like to take the time to open up the floor for discussion and questions.
Okay, our project was the ventilation and the VOC levels in older and newer houses, and this is Sam Lidstrom, Ali Dombrowski, Lubo, the lovely Stephen Tuttle, and Anthony Lasitra.
Here's a quick synopsis of our presentation. Sam's going to talk about the question and purpose and our hypothesis, and then I'm going to give you a quick overview of why we chose chlorinated benzenes and proper ventilation strategies for each household. And then Sam will then proceed to tell you about the procedure and results in conclusion. Go ahead, Anthony. Go ahead.
Okay, our question was, how does the ventilation of old houses versus new houses affect the concentration of chlorinated benzenes? And our old houses were considered over 30 years old, and our new houses were considered 20 years and below.
Okay. Our hypothesis was that the inside readings of older houses would have significantly higher concentrations of chlorinated benzenes than new houses because of poor ventilation. And we chose to do this in the winter months because that way all doors and windows would be closed, and most likely, so that we wouldn't have that variable in there. And we also did this because of the newer ventilation strategies didn't include opening doors and windows, as were the older ones did.
So the three chlorinated benzenes that showed up in our data were chlorobenzene, 1,4-dichlorobenzene, and 1,2,4-trichlorobenzene, which the previous group talked about. Just a quick overview. Chlorobenzene is found in pesticides, and it's used as a degreaser and to make other chemicals, and it readily evaporates into the air. And you can be exposed to chlorobenzene in many different ways, either like drinking contaminated water, breathing in chlorinated benzene vapors, or skin contact either directly or through contaminated soil. This causes headaches, nausea, sleepiness, numbness, and vomiting, and the more severe, let's try that. Side effects are liver, kidney, and central nervous system damages. And the Occupational Safety and Health Administration suggested that anything over 75 parts per million in an 8-hour day workplace would be considered dangerous. And so we decided that most people are in their house at least 8 hours, either sleeping or people like working in their houses, either like housewives or people who actually just do work in their houses. 1,4-dichlorobenzene, it's found in air fresheners, mothballs, and toilet deodorizer blocks. And you know what those look like. Anyways, when exposed to air, they slowly change from a solid to a vapor. And if you're breathing those vapors from the previously mentioned products, that's the main means of exposure. They cause irritation to the eyes and nose and upset stomach, dizziness, and then also liver and kidney problems. And it's also considered to be carcinogenic. And then 1,2,4-trichlorobenzene, which was discussed pretty thoroughly, again found in dye carriers in herbicides and insecticides. Also, it readily evaporates into the air, and it causes irritation of the lungs and coughing, and also liver effects. Go ahead. So those are pictures of those. Just a quick overview of like proper ventilation strategies in each household. Obviously, you want to have good ventilation in your houses for the health and comfort of the occupants, to ensure safe and efficient operation of combustion appliances, to control condensation and moisture vapor removal, and obviously to remove pollution and odor from your air. Background ventilation is finely controlled ventilation, mostly found as trickle ventilation, and it's aimed at providing fresh air in each room in the house. So most houses have that. Rapid ventilation, it's pretty self-explanatory, provides short-term high rates of ventilation in individual rooms on demand. So opening the doors or opening the windows is how that happens. And extract ventilation is another form of rapid ventilation that's provided in rooms that are more susceptible to odors and moisture, including like the kitchens and the bathroom. And it's usually provided by fans, but in the newer houses, PSV, which stands for passive stack ventilation, is more energy efficient just because it turns itself on through humidity sensors, and it uses less energy. Go ahead.
So to test our hypothesis, we first had to choose our old and new houses that we were going to research. We used all the data that we collected in our 2 chemistry classes at Big Sky just for the winter months, so that that variable would be controlled for the most part of closed windows and doors. We came up with 7 old houses, which we defined to be older than 30 years, and 7 new houses, which we defined to be newer than 20 years. The reason we can only find 7 for each is because there were lots of houses that either were in between that 20 and 30 year window, or there was some houses that were older but had been renovated recently, and we didn't know if that would throw an unexpected variable into our research, so we threw those ones out. After we found the averages of each the old and the new houses in the 3 chlorinated benzenes, we determined whether or not there was any statistical significance to make our conclusion. Okay. Well, the first thing we found that was kind of weird was that there were no readings of 1,4-dichlorobenzene in any of the old or new houses. So that was kind of insignificant, I guess. But we did find higher readings of both chlorobenzene and 1,2,4-trichlorobenzene in newer houses. So there was evidence that there were higher levels. But when we performed the t-test, we found that these were statistically insignificant because the t-values were between 10 and 15% for each. So, go ahead. In conclusion, we really weren't able to conclude that newer houses had any higher concentrations of chlorinated benzenes because there was no statistical significance as we found in the t-test. Although we did find evidence that levels were higher, it would not be valid to conclude that this was the case. Reasons for this, we thought there might be many different factors that we hadn't counted on before. When we first decided to do this, we counted on ventilation in newer houses, not including doors and windows, but including newer systems such as trickle ventilation that had not been used in older houses. We did not think about natural air infiltration in older houses, such as gaps in the building fabric, because there are higher energy efficiency standards now, and that could have caused an unexpected trickle ventilation in older houses. We also, due to we had the time limits that we had, older than 30 years and newer than 20 years. We did have a limited database because we could not use all the data that we had. And a lot of the data was incomplete for some of the winter houses. And we also could have used more compounds than just the 3 chlorinated benzenes, which could have given us a more accurate conclusion. So if we were to do this again, we'd probably look over a wider database, first of all, and choose more compounds to conclude from. Is there any questions?
All right. Sorry. So first I'm just going to ask you to bear with me because I've never seen this PowerPoint before, so we're going to try to go through it. And so I'm going to start off by introducing everybody. This is Andrew Lowney, Connor O'Neill, Shane behind me, Ty here, and I'm Costco. And so I guess we did this PowerPoint on 1,4-dimethylbenzene and toluene, actually inside and outside the house. And so our question was, why was the concentration of toluene and 1,4-dimethylbenzene higher inside the house than outside? Our hypothesis was that we believed that there were more concentrations inside the house because toluene and 1,4-dimethylbenzene are used in paint products like nail polishes, and there was pretty much more of that inside the house than there is outside. And so we had the same common procedure. We investigated with the pumps and researched and was able to use the data to figure out the levels of toluene and dimethylbenzene in the house. And so toluene is used in all kinds of things. You see if they're explosives like TNT, which is pretty cool, dyes, gasoline, and industrial solvents. 1,4-dimethylbenzene is also used in solvents, making drugs, insecticides, enamels, and gasoline. Are we almost done? What? So there's also illicit uses of this stuff. Both products are used as solvents in the production of cocaine, amphetamines, and methamphetamines. Toluene is also found in LSD and two big long words.
Okay, so you're gonna have to bear with us because we lost some of our slides, so we don't have like any data or anything. But we kind of do though, because thanks to Emily, we got some of her data for our houses. Like what we did was we just took the results from all 5 of our houses, and so Connor's was the highest in particulate matter, which was like 1,400. And we found the reason for this is because when he did his little testing, his mom just painted her nails. So he says, and then Ty right here's was the lowest, and his was at 135. And he said he just put it in the living room, and there was no effects to it. And then Andrew's was the second highest, and he just painted his house a couple months ago, so that's why it's high in there. And then all of ours were pretty low outside. Because there's more air, or there's a lot more air that this stuff could go into. And so we found higher concentrations of both toluene and 1,4-dimethylbenzene inside than outside. This was a result of fresh paint inside one student's house and fresh nail polish in another. Both are used as cleaning agents, pesticides, and paints and varnishes. And that's our presentation.
Hey.
What?
And we'd like to open the floor to questions, but our answers will be rather ridiculous, so I just warn you now. There probably is, but we didn't spend enough time to find out what it was.
It's paraxylene, I believe. All right.
Thanks,
All right, thank you very much.
While Kayla's getting up here, I just wanted to thank you guys for coming. This is more than we could possibly have imagined 3 years ago when we conceptualized this symposium. Kayla, I just want to briefly introduce. Kayla is working on a kind of new component of this project, which is monitoring PM 2.5. And it's something that's we're going to be seeing on the horizon probably more and more in this project. But she and a collaborator here, Emily, took a whack at it this year and came up with some interesting results that we thought you'd want to see. Kayla.
Yeah, my name is Kayla. I'm a senior. I did VOC sampling last year in chemistry, and this year I'm continuing with PM 2.5. So it's estimated that at least 90 million Americans live in areas that don't meet air quality standards for some pollutant. Particulate matter is one of 6 criteria pollutants that have had standards set for them by the EPA. Particle pollution are particles made up of solids and droplets in the air and can be composed of acids, allergens, dust, dirt, smoke. The particles are characterized according to their size. PM10 are coarse particles. They're larger and can be sized between 2.5 and 10 microns. And they usually get trapped in your nose or throat, and so they're removed by mucus and don't really have as many health effects associated with them. PM 2.5 are smaller, they're less than 2.5 microns, so they're able to travel through smaller airways, get deeper into your lungs, potentially causing a greater risk. Outdoor sources include motor vehicles. Diesel particles are extremely small. Power plants, wood burning, and other industrial processes. Indoor sources, tobacco smoke is a prime source of particulates. Also cooking and things like burning candles and wood stoves and fireplaces. Short-term effects, coughing, sneezing, difficulty breathing, irritation of like your lungs. And then with long-term effects like bronchitis, reduced lung function, and several cardiovascular conditions, including heart failure and arrhythmias. So here we have a picture of the sampling equipment. There's the pump, and the red thing is the environmental monitor, and that's where the filter is. So a student takes the pump home, sets it up in hopefully like a high traffic area in their house. It runs for 24 hours, and the particles get pulled through the filter, and only the PM 2.5 particles get trapped on the filter. Any larger particulates get blown back out. So I went through the questionnaires that the students filled out at the beginning of the year and looked for houses that I thought would have high levels and houses that I thought would have low levels. High levels being houses with like smokers, living near busy intersections, dirt roads, things like that, and then seeing how much of a difference there was in between them. We have 7 filters that have been sent back from the lab, and so we have final concentrations for them. You find the concentrations of the particulate by taking the weight of the filter, which is in micrograms, dividing it by the total flow of the pump during the 24-hour period, which is in cubic meters, to get the concentration in micrograms per cubic meter. As you can see, some are really low and some are really high. The highest one, not really sure why it's so high because there's nothing indicated on the questionnaire why it should be that way. But like ones like 176 and 133 could be, they live near like busy roads and a dirt road, so I think the dust particles probably contribute to that. There are standards for PM 2.5, a 24-hour standard of 65 micrograms per cubic meter. None of our samples came close, which is good, but still be interesting to see what actually caused these higher levels. I'd like to thank my teachers, Mr. Jones and Mr. Harkins, Tony Ward at the University of Montana, who's my mentor, Emily Weiler, who taught me how to use the pump, and especially the Big Sky chemistry students for tolerating and cooperating with the loud pumps. As this was the first year this project was done, so hopefully next year we can get started earlier in the year and make comparisons between like fall and winter samples and see how they differ, and also getting pictures of the filters and then getting a chemical analysis of them to see what the particles trapped on the filters are composed of. So.
So I guess now that concludes the end of the Big Sky presentations. $10,000 award from Toyota Tapestry Grant to do PM sampling at Corvallis High School next year. So Jim. So unfortunately, 2 of our judges had to bail out on us. They have to go to work now after being at work all day long with us. But we still have 3 of our judges left. And I'd like to take a few minutes and kind of show our appreciation to these guys. And if you would like to, you 3 guys come on up and let's turn the lights on here. Okay. So first off, we have Mayor Ingen.
Oh, thank you very much.
And I'm actually gonna. Thanks a lot, Mayor Ingen, for being here.
Thank you.
And if you want to say something, I'm gonna put you on the spot here. That's coming your way too. Just
Don't need to put me on the spot. I'm just remarkably impressed with your efforts and some of your senses of humor today, ladies and gentlemen. So thank you very much. It's been a pleasure to be with you, and keep up the good work.
Mayor Ingen, everybody. Next up, we have Coach Hout, Bobby Hout.
Thanks, Nancy. Thanks for being with us.
So thanks a lot.
Appreciate it.
Yeah, appreciate you being here. And if you want to say a few words, real
I'll
fast.
be short-winded, but it's great for me to get out and do something that's a little more academic in nature. It seems like not too long ago that I was attending this university. It's a great campus. You can see that day out there, and I hope that a lot of you, many of you, will choose to come back here and go to school over the next few years. So it was great having you, and welcome to our campus.
So last but certainly not least is Garen G Wiz or Garen the Wizard Smith. Mr. Question and Answer. So Garen, thanks a lot for being a judge with us.
Yeah, thank you.
And I've worked for Garen and now with Garen for since 1997. So I actually came up here to Montana to work with Garen from Texas. So he was my boss for a long time, and now I get to work with Garen.
You guys are a lot less expensive samplers than Tony was, so. We really couldn't do all of this sampling with just students over here at the university. It would cost way too much for the transportation and getting those people spread out on all those days. So you really are vital to our collecting a wide network of data, and we're going to try to put it together and get a much bigger story. So you're going to be the words in the chapters. So thank you very much.
All right, Joel and Ludus, come on down. Just as you walk back in. We've been waiting for you. No, this is, we're just giving thank yous to everybody. This is perfect timing. So we really appreciate Joellen coming in from University of Washington, and I thought she did a great keynote address this morning. And we're actually going for the trifecta with Joellen. We're hitting her up for a technical seminar from 3 to 4, and then a town hall meeting from 7 to 8 tonight. So if you guys want to go home and tell your parents, saw this awesome lady this morning from University of Washington talking about air quality and the health effects of poor air quality. It's going to be a really roll up your sleeves, get down and dirty discussion on air quality, and or maybe not that.
By 8 or 9, I should be completely wiped out.
But it should be a lot of fun tonight. It's from 7 to 8 back here in the Urey Lecture Hall if you want to come and ask some questions to Dr. Ludus here. But we would like to give you a whole bunch of free stuff.
So do I get to be a grizzly? Woo-woo!
Honorary grizzly.
Thank you. Everybody wants to be a grizzly. Oh, I know.
Thank you.
I'm really impressed with all the students.
Do you want to say something real fast?
Well, just that I was very impressed with the students and their efforts, and keep it up. Hope you turn into a lot of good scientists. We need you.
Okay, now I'd like to recognize the people who make this thing go, and that's mainly the teachers. And first off, where's Melissa? Melissa, come on down. Okay. So Melissa Henthorn is the Hellgate High School teacher. And so this is her second year in the program, and we look forward to many more years. And thanks a lot, Melissa. We're going to ask you to stay up here just for a second. We're going to give out awards. So Jim Strebel from Corvallis High School. So Jim is in the second year of the program as well, and he's been great to work with. He's a lot of fun, and thanks a lot, Jim.
You bet. Thank you, guys. Great.
I'm forgetting somebody. Come on, Dave. Come on down. Ty. So Dave is are you still the reigning Northwest Teacher of the Year? Science Teacher of the Year? Okay. So this is the former Northwest Teacher of the Year. Science Teacher of the Year. So now I think that Judge Wrangler, we have the final results. The moment of truth. Dave Jones, please report to the podium.
So what are they saying, the names of the winning team, Tony? Not, okay.
So the first off, best presentation at Hellgate is?
Okay. It's Deanne Snyder, Robin Green, and Brendan Harrell. Come on down.
So the award is $150 at the Grizz bookstore. Melissa, do you want to say something about these guys? Okay, we're going to keep it moving. So next up we have Big Sky High School.
Let's see, and the winners are Amy Smith, Steph Seawald, Megan Taylor, Jesse Ponton, and Cheryl Fredericks.
That's all took care of. And this is the prize. I know. Good job, guys. So obviously the last award goes to Corvallis High School. And what we haven't told you is that the last award goes to the best overall presentation as well. And we've thrown in an extra bit of money for this, and so this is a $200 award to the gift certificate to the UC bookstore. And the winner is?
I can't read this here. It goes to Ocean, Colin, and Nathan, the Walking Conch.
Thank you. All right. Thanks a lot, teachers. It's been great. Okay, so before you guys get out of here, we have to do a couple things. We have to do evaluations first, and we also have to thank the people that made this happen today. And first off, let me thank CEHS, the Center for Environmental Sciences, and the Department of Chemistry for allowing us to grow this program over the last several years. Andre, thank you. And thanks to the Chemistry Department. Also, thank you to Montana Department of Environmental Quality, Bonnie Rouse, for helping us bring Dr. Ludis out. Bonnie. Okay, Bonnie, come on down. Andre, come on down. Yep, they're thrilled. Thanks, Coach Hack.
Thank you, guys. Thanks, Coach Hack. Thanks, Nancy.
We'd also like to thank the National Science Foundation, EPSCoR program, the National Institute of Health, National Center for Research Resources, and Dr. John Shumpert, who is not here right now. His company, Resources for Environmental Occupational Health. Dr. John Shumpert is a medical doctor here in town, and he helped fund this program this year. He provided funds for the whole thing. So I would like to specifically thank John Shumpert for everything. And big round of applause for John. So thanks a lot, guys. Thanks for doing this, and we'll see you next